Very good morning to everyone on the third day of this wonderful event. The session now has some kind of EEO systems, data systems kind of name, but I wanted to address this crowd in the sense that originally this was kind of formed from a basis of Arctic Passion, which was a wonderful EU project for 4.5 years where a lot of people had fun. And I think the name helped already it, but that's why I thought even after the project we could have something like this session to join this, and I think about half of the presentations are from the kind of community that was involved. These are not necessarily actions from Arctic Passion at all, but the community we try to keep together in these kind of sessions. So, very warm welcome, and Ilkka Rinne from Spatineo is the first one. Good example, like Spatineo was in Arctic Passion, but what Ilkka will present is a different thing. But I think this is a good way of trying to keep communities after projects alive. Ilkka, go ahead.
Good morning. Everyone, it's good to see you all here. It works better now. Yes. Okay, so my name is Ilkka Rinne. I'm the founder of our company, Spatineo, and also a product owner of our new product, Spatineo Discovery. So I'm going to be talking a bit on the user side this morning, on how to actually get access to data. I know that many of you are probably working with providing the data, using the instruments, doing the math calculations, whatever, in order to get the data out to the users. And my perspective, a bit different this morning, is how can you actually, as a data user, get access to the data? So probably, if you go to the mindset of the data user who really needs good quality data sets for running their projects, the issue is in many times that it's really difficult to find the right data out there, especially with the explosion of EO data products coming every month. It's really difficult to find what you actually need for your data. Maybe what you did 1 year ago doesn't apply anymore if you're not tapped into the flow of new data sets coming that could be relevant for you. And as you probably know, the principle garbage in, garbage out. So your end results of your analysis can only be as good as your input data. So you need to be able to spend the right amount of time for finding the data you need that is relevant for your task, but not too long, because all the time that you spend in finding the data is taken out from the actually interesting part of your work that you're really, really good at, being the analysis itself. So it can take, weeks to months maybe, depending on your project, to actually make sure that you have good enough data to start your analysis. And that's an issue for many of the users also. They might not be familiar with all the data formats and the APIs and all the portals that you need to go through to actually find what you need and be able to access it, use it, and it can be frustrating. So, if you do it right these days, you are spending more time searching for data than using it, which is twisted. Shouldn't be like that. But you have to do it in order to compete with whether you're running a successful research group or a consulting company. You need to be able to be as good as your competition in order to get research funding, in order to get good quality papers, in order to be able to charge your customers more for your consulting than your competition. And this is all based on your knowledge, but it's also based on your ability to spend enough time in in the actual analysis to make good quality work. And most of us are not very interested in searching the data. That's boring. So we're trying to fix this with like 3 principles in Spatina Discovery. And I think we are doing pretty good. The first is our search engine for data is trying very hard to understand the user intent first. So you don't have to know exactly what the data is that you need to find, the right keywords, but you say that this is the problem I'm trying to solve, and you start with that. So as an example, you probably know there was this huge wildfires in Los Angeles about a year ago, and there was a lot of search and rescue activity, fire extinguishing activity going on, and you need to coordinate all this. And they didn't have Spatina Discovery, but if they had, it could have worked like this. So you say that this is the task that I'm working with. Tell me what I need to, how do I start the search? So Spatina Discovery, it suggests you, based on your task description, it suggests you data categories that you can use for the actual search, and as well as analyzing the areas of interest that are probably relevant for solving your task. So if I choose one of them, I get forward. I can start actually finding the relevant high-quality data sets. So I choose one of the categories. I immediately get metadata descriptions, rich enough so you can actually determine whether this data set is relevant for solving your task. And finally, when you say that, okay, it looks good, it's also live, it seems to be working, we are doing live monitoring of the data sets, of the APIs behind providing those data sets, you can just add that to your map on your GIS application with one click. So the third part, get to the interesting work fast. That's really, I mean, nobody cares about people working with Google and us, we care about finding the data, but it's not your bread and butter. Your bread and butter starts when you actually have the data and you can get to the interesting stuff. When comparing Spatina Discovery to some of the products that we know that people are using, currently Google Search, it's very nice, and it covers like maybe not the whole internet, but a lot. The problem is that you only get pointers to the portals, usually websites, and you need to go the last mile to actually get to the data. With tools like SReact, GIS Online, Living Atlas, you get a nice catalog, but it's not very broad, doesn't have a lot of open data there, and you need to be able to search by the right keywords. So it's not very smart. I know they're working with it, but currently that's the status quo. And there are a lot of these open data portals, catalog services, Sentinel Hub, for example, ESA Mars Explorer. And it's really good if you're really expert on EO. You know how to get there, you know how to work with the different instruments and data sets. You can browse that. It's pretty complicated as a search engine, but it gets you there if you know what you're looking for. And then there's, of course, in the age of AI, ChatGPT, Gemini, the Gen AI tools. It's also very useful, but it doesn't really provide you with the access to the data. So you still have to do the same kind of stuff that with Google Search in order to get there. Some of the design challenges that we've tackled in developing this is that, I mean, it's not easy to understand the user intent, but it's surprisingly much easier now with Gen AI than 5 years ago. So this is one of the peak drivers for us to be able to develop this product, that this is something that we can actually solve now much easier with much less code than was previously possible. And of course, you also need to be able to create a good search engine, efficient search engine that is able to combine traditional keyword searching on the metadata with the AI age, vector search, relevance search stuff that's also developed a lot because of the AI boom. So we can harvest the fruits of that kind of development in the product. And from the user point of view, is very, very necessary and very, very, very important to be able to streamline the user interface that you can actually get very easily to the work as mentioned before. So that, for us, that means that we need to go to the platform where the GIS analysis is done. For example, the ArcGIS Pro desktop. We're not great fans of Windows coding, but we need to go there because that's where the users are. And we need to integrate very tightly to the GIS applications in order to streamline the user experience. We are working with the Pioneer community right now, so we have about 1,000 people on the wait list interested for joining and testing this out. And we have a Pioneer program for them to be able to do beta testing, early access, and so on. And we will actually start the beta testing tomorrow with the group. So if you want to be part of that, please come to me. I can still slip you in. It's now closed with the actual beta testing program, but I think I can add 1 or 2 people if you want to be there. It starts tomorrow, and we are expecting public release in March. So we're starting with the ArcGIS platform because there's a lot of existing potential there, a lot of users that are also accustomed to the pricing model. So it's not going to be an openly available free product, unfortunately, because we need to make business also. But it's going to be a subscription model, and people already on the S3 platform are probably much more accustomed to that kind of model that when you need to do, you need to pay subscription price monthly or yearly. And we are moving forward to providing more than just the open data sets, commercially available APIs, so you can just subscribe through our application. So it's similar to, let's say, streaming services these days, or Apple Store or something like that. You can just, with a few clicks, you can add a commercial API subscription to your service and get charged from that. So we are also very interested in talking with any of the data providers who are willing to provide their data for a service fee, for a subscription, in order to integrate into this. So with that, I'm closing. Thanks for listening, and grab my sleeve, or Oskari, our CEO, is also here today. So yeah. With that, thank you.
Thank you, Ilkka. And maybe we have one quick question if somebody has. So.
Thank you. Thank you. Hello. Okay, now it's working. Thanks. Very interesting. So I wonder when the cookies version will be planned and available. Thanks.
Yes, that's a very good question, interesting question. We've been thinking on the platforms and how do we do that. So as mentioned, we are starting on the S3 platform, but we've been thinking of other, like GIS is definitely one of the key open source alternatives out there. And we don't have a schedule or exact plan for that, whether we'll do that development ourselves or we will do that through our partner or someone else who's very already into that ecosystem. So that's one option. So, well, we don't have a plan, but that's definitely on the roadmap.
Yeah. Okay. So my question is very simple in the sense that I think coming from a weather service, one bridge is many times missing is that the GIS stuff is somehow organized, and then meteorological or kind of weather forecasting stuff is a little bit kind of other ways organized. And I know that some weather services do this kind of like API support on that side, but there's a whole lot more that is not tapped in. Do you have any plans for kind of tapping into that part? Because I think that gives you the future more than just yesterday.
Yes, that's also a very good question. I think also the weather and the climate community is doing a lot of this good standardization. One example is Stack, which is a very good way to publish your EO datasets, for example. It could be also weather model results and something like that, which are big raster stuff. And that is definitely on our roadmap to include there. So you could publish your Stack catalog, and we could include it in Spartina Discovery.
Okay, thank you for the questions and answers. And next we have in the program Matthias telling more about how Sentinel-1 data can be utilized to analyze snow.
Yeah. So good morning. Yeah, I'm Matthias Pavet. I work at the WSL Institute for Snow and Avalanche Research in Davos in Switzerland. And actually here, it's not directly my work, it's the work of my PhD student, Francesca Carletti. Obviously, I'm supervising, I'm taking part into this work, but this is really the focus of her PhD. And this is done with our colleagues from EURAC in Italy. And the goal is really looking at what are the drivers for Sentinel-1 backscatter during snowmelt. And here, so just a quick recap on Sentinel-1 SAR. Most probably you know everything about it already, but so this is a constellation of some number of satellites. Unfortunately, we just happened to be using it when it was only one satellite. That was bad luck. For us in the Alps, we have a recording if we combine all the orbits every more or less 3 days. And the footprint is 20 by 20 meters. And just as a reminder, it's 5.4 gigahertz. What it means practically is that if you take dry snow, it's mostly transparent at 5.4 gigahertz. And you have strong backscattering on the ground and some volume scattering in between. If you take wet snow, everything is mostly absorbed on the very surface. And so it's often used as a way to distinguish between wet snow and dry and melting snow, which is very useful. But then we looked at this paper from one of our colleagues at EURAC, and he was looking at first what is the typical development during a snow season of snow parameters like snow water equivalent, so basically the mass of snow that you have on the ground, and liquid water content. So you have here the snow water equivalent that is in red, and the liquid water content here in yellow. So liquid water content, this is the water that is in liquid form within your snowpack. And you have some phases, actually. So the first phase that you see here is the dry snowpack. You just accumulate snow. Then you have a moistening. This is when you start to have some melt refreeze on the surface. So you have some liquid water content, and then it refreezes at night. At some point, you have a wetting front that develops, and this is a ripening of snowpack. But snow cannot refreeze totally every night, and you start to have this wetting front going down into the snowpack. And then at some point, this wetting front is going to reach the ground, and this is the start of a runoff. The liquid water is able to escape the snowpack and go into the ground. And now if I superpose here, actually, the backscatter signal from Sentinel, and I take here 2 tracks, the one from the morning, the one from the afternoon. It seems to show some correlation, some behavior that is similar to what you see happening into the snow. And actually, if you take some thresholds, like first time that your afternoon signal is going to decrease by a given amount, it matches the beginning of the moistening season. If you look at the same decrease, but on the morning track here in green, it matches the beginning of a ripening. And if you look at the minimum of these two signals, because they reach a minimum and then go back up, it's the start of a runoff. So for us, it was really the starting question from this. It was, can we assimilate the Sentinel-1 backscattering data in order to improve the modeling of the snowmelt dynamics? Or more or less, can we do more than just distinguishing between dry snow and wet snow? And we're hoping for more, of course. So there's a very typical Swiss way of dealing with difficult questions. When you have a difficult question, you don't know what to do, then you just start digging. And so we did dig. 85 full snow profiles over 2 winters, in winter 2023 and 2024. You can see here an example of profile. Another example of profile, this one was easy, it's the end of a season. Here an example of profiles, we did lots of measurements, it was a complete mess, lots of measurements were not working properly, we had to redo over and over and over again. We did profiles up to 3 times per week during the melt season. Needless to say, we didn't need any gym subscription. I told the people I hired for this, it's embedded, it's already part of it, part of the package. What we measured the total snow water equivalent. We measured the density every 3 centimeters. This is what you see here with these holes here. We measured the specific surface area every 4 centimeters. We measured the liquid water content with denotometer every 2 centimeters. We measured the liquid water content with melting calorimetry every 10 centimeters. Measured the temperature every 5 centimeters. We took pictures of a profile, like here, with near-infrared cameras. We measured the surface roughness. Maybe just one quick word about where we did it. It's our field site on Weißflur, so it's above Davos in Switzerland. It's intra-alpine climate. It's located at 2,536 meters. You see a picture of a field site here. Our office is just on the valley here. For us, it's very convenient because just a few hundred meters to walk, and then we take a ski lift and we come here. Snow measurements have been done here since 1936. And we have access to power grid. We have fiber internet. We have Wi-Fi. So you can imagine we can just put as many sensors as we want. It's free for all. Among these sensors that we have, the ones that are relevant for this project, we have automatic snow height measurement. We have a snow fox to measure snow water equivalent, also a snow scale, also a lysimeter for the runoff. We have also daily manual measurement of snow height and new snow amount. We have also bi-weekly snow profiles. And we delimited an additional area for our project here on the south part of 20 by 40 meters. And we have a few special measurements where I want to say more. One of them is about surface roughness. So what we had first is an automated laser scanner. Every hour it does a scan of a surface. Resolution is a few millimeters of accuracy, and with 1 centimeter or slightly less of horizontal resolution. Then we did also Charuco board pictures. Basically, this is this board that you see here, like here, this black panel, that you put it into the snow. We put it 3 times with the same orientations, then 3 times at 45 degrees, and then 3 times at 90 degrees. Take all of these pictures, then we perspective correct the pictures. We can follow, with machine learning, we can follow the snow line, and then we can extract a measure of the roughness. And you can see more on this paper. You will see all the references in the end, actually, so you'll get it in the end. We did also special measurement about liquid water content. The first kind of measurement, the denotometer, you measure capacitance, so it gives you the dielectric permittivity, and this one actually depends on the liquid water content that you have in your snow. The melting calorimetry, it's a different principle. It's basically how a known mass of water is going to change its temperature when you melt a known mass of snow with an unknown liquid water content. You can see here we have hot water, we have a thermometer into a thermos bottle, and then we can do the measurement. It's very time consuming, but it's quite accurate. And again, there's a paper about it that we wrote. This is this one. You will see the reference in the end. So now a quick overview on the results. I take the example of winter 2023, and it was a record low snow height. What you see on the top here, so this is here the density with a snow cutter. Here you see the liquid water content with a denote. Here you see the liquid water content with calorimetry, and we did actually many more calorimetry measurement in 2024. It was much more systematic. Here you see the snow temperature, and here this is the specific surface area. And the roughness is not shown here, you'll see it afterwards. In 2024, we had to reduce to only twice a week for the profiles because it was a record snow height. Now let's look at the results of the data. Let's compare the ground truth with Sentinel-1 backscatter. What we have on this graph, we have the two passes, the afternoon one and the morning one here. The triangles, this is the measurement points of Sentinel. And the shaded area, this is just linear interpolation between the points. And here, this is our data. Gray area here, this is the snow height. You have a development of a season. So here we have a temperature. Here we have a liquid water content. Here we have a snow water equivalent with dot. This is what we measured in the profile. The line, this is a measurement with a snow fox just a few meters apart. And then you have here the runoff measured by the lysimeter. And here below, you have a surface roughness with charcoal board. If we look at first the moistening season, then we can see already some interesting things. Because it's very, very sensitive. Sentinel is very sensitive to liquid water content. You can see here, the first time we start to see some liquid water content on the very top, and it's actually not so much. We have a strong drop already on the signal, strong absorption. The second one is that actually we have already some runoff here, which is because of preferential flow. Now, if we move to the later period of really what is the runoff, when we have this increase on the backscatter signal, what we can say is that actually this monotonous increase is not linked to runoff. Because runoff started much earlier already, we see here we have some runoff already, but this is here the increase of the surface roughness that produces it when the snow is wet. So saying that the minimum of the backscatter signal from Sentinel is the start of a runoff is actually not true. The second approach that we use, it was with SMRT. SMRT is a model that simulates the active-passive microwave response from layered snowpacks. And it's modular, so it can combine different electromagnetic models, different microstructures, and permittivity formulations. You can see more on this paper. And here, so I just focus on the melting season. So it's the backscatter signal again, because for dry snow, it just works with no problem. And here, this is what we simulated with SMRT. The box plots, this is the variability introduced by assuming 1% of liquid water content uncertainty into each layer. What you can see in the first period here, this is when the moistening, we're starting to get more and more liquid water content, and the surface is smooth. SMRT is just way off. Next period here, we have the first development of some surface roughness. It's still very small, but we have some surface roughness. And you see SMRT is getting much closer to what the satellite sees. The next period here, it's interesting because we had a new snowfall. So the roughness is buried. Roughness as seen from the satellite, it's very smooth again. But we still have lots of liquid water content into the snowpack. SMRT is way off. And the next period here, we have a decrease of the total liquid water content because the snow is really melting. Lots of water is running out of the snowpack. But we have a strong increase on the roughness. This is the development of the sun cups. And SMRT is again on spot, properly simulating what we see from the satellite. So we have basically here two phases. One is wetness dominated and one is roughness dominated. And what we can see is that SMRT, it's working well for simulating the dry phase. It's working well for simulating when this is roughness dominated. It's working very badly when this is wetness dominated. So it brings me to my conclusion. Overall, we built a high-resolution ground truth dataset about radar and snow interaction. And here I want to show that actually remote sensing, it's just very interesting. I've seen here so many cool stuff with satellite and so, but we need to have ground data too. The SMRT model struggles for wet snow-dominated regime, and actually there's a reason for it. It's that the dielectric permittivity models of wet snow for this kind of frequencies, and actually quite a large range around it, are not appropriate. And here I show you two different formulations So this is as a function of a frequency. You have a dielectric permittivity for two different formulations. For snow that is quite high density, this is typical snow in the end of a season when it starts to melt, and with 8% liquid water content. And you see the big difference in permittivity. And of course, if we swap between these two models, actually by taking the H86, then we would simulate properly what the Sentinel sees. But it would introduce all the physical inconsistency into the model. We can ask us why we have that thing, and it brings us to the new questions and future work. Is that actually the shape of the water inclusions in snow as a function of the liquid water content influences the dielectric permittivity at these frequencies. But we have no clue. Nobody knows how the water inclusions are done into this the snowpack as a function of liquid water content. And the last question is, what are the drivers for surface roughness development? Or more or less, how do sun cups form? I thank you, and I give you here so the references I promised for everything. And thank you very much for your attention.
Thank you very much. Maybe we have time for one quick question. Mikko?
Thank you very much, Matthias. So in Finland, this is very interesting in the sense that we have more Sentinel-1 opportunities because we are more up north. But we do have less snow, so it's not that big, and it's not as like one season in a certain rhythm, but there's much more this up and down. Do you think that there's a possibility to some parts of this kind of wetness kind of slowing down? I think the drying in between, that dry snow comes on the top. That's one of those things that we'd like to better thing. Do you see that that's possible with Sentinel-1?
I guess partially, except that you might have a problem still. When you say dry snow, it's, as we've seen, as soon as you have a little bit of liquid water content, it's over, you have very, very strong absorption. So you will still have some dry snow, but you might still have a little bit of liquid water content, and you have already this very strong absorption. So it's the same problem. I think it would make sense to reinforce, this is really the focus for future work, to look at this dielectric permittivity, to understand exactly how it is, and to be able to understand much more and to get much more out of this backscatter signal. Because right now, basically, we have a nice signal, and we understand pretty much nothing about it because we are not able to reproduce what it sees.
Thank you.
Thank you very much, and maybe one more applause to the presentation. Next in program, we have Juliette Ordet. So, please. We learn about what happens under the snow.
So hey, many thanks, Matthias, for introducing all the snow subjects. Oh. Okay, so quite happy to present my work for the very first time here in Finland. So this is a work that I started as a PhD student earlier between France and Canada. And now we're going from Switzerland directly a bit northern to the Arctic area. In this work, we focused, so as the introducer said, not directly on the snow, but what's happening below the snowpack. And here we are presenting quite new and interesting database of 14 years of ground temperature below the snowpack that was retrieved thanks to L-band passive microwave satellite observations. So just few words about the Arctic area. So what I call Arctic here, I'm mostly focusing above the tree line. So I mean where there is no trees anymore, only shrubs, mosses, lichens. And as you can see, it fits quite well with where we can find circumpolar permafrost. So permafrost is this frozen ground you can find where, I mean, it's fully frozen for 2 consecutive years, but you have on top this active layer that is subject to annual thawing and freezing. And a key parameters to know more about the state of this active layer is the ground temperature. And in fact, as you all know, this is drastically facing climate change, averaging in average 4 times more than the whole globe. And here we are focusing on what's happening on the ground temperature during winter time. Because on the right, you have these figures try to sum up what are the consequences of climate change, so warming, vegetation growth, and increased precipitation in the Arctic to this ground temperature. And you can see that, well, depending on the processes, you can have either increase or decrease the temperature, and the situation is not very clear. And this we can retrieve also in the modeled ground temperature for nowadays. They are showing quite a huge bias based on this study where the figure on the left is extracted from Errington. And the thing is, like, what is quite challenging here in winter, that in the Arctic, we have snow all over the area. So we don't have direct access to the ground temperature. And moreover, this snow is acting as a thermal insulator. So it's quite difficult to predict what's going on below the snowpack and how the ground is acting. So here our research question was, in this context of climate change, what is exactly the spatial and temporal evolution of ground temperature under the snowpack in the whole Arctic permafrost area, like not only locally, but like in the whole area. And the objective was then to find new observation methods to monitor the state of this ground temperature in the Arctic. So as analyzed by Bartsch in 2023, there is now a lot of new methods to monitor the permafrost thanks to satellite imageries. And here we propose to use passive microwave remote sensing to deal with that. And more precisely, we are working with the SMOS satellite mission that some of you might know. This is an ESA mission that was launched in 2010, so we also have quite a long time series, which is super interesting to have this kind of climate-related studies. So basically, how does SMOS works? It's a radiometer, interferometer, radiometer, measuring some brightness temperature. And we can relate this brightness temperature, thanks to emissivity, to the effective temperature of the observed scene. And this is what we are looking for, like the temperature of the scene. And operating at L-band, so 1.4 gigahertz, this is very much sensitive to liquid water, but then in wintertime, you have a full transmission through dry snow, as Matthias just explained before. So in 2025, we proposed the first methods based on this snow transparency to retrieve the ground temperature. So on the left, you have like a scheme of the scene that we are considering, so just some snow and an active layer where we want to define what is the ground temperature there. Then we moved it into a model, like you can see in the middle. And thanks to that, so we compared the result that we have for the 14 years of SMOS on 21 sites, including 8 sites where there were no water bodies, because you might also know that there was a lot of lakes and water bodies in the whole Arctic, but it's a bit more special, so we go back to this later. And when you were focusing to these places where it's no water fraction, as you can see on the right, you have like the results and the performance of our model on the left compared to what the ground temperature from ERA 5 are showing. So you can see that in both cases we have a bias close to 0, which is nice, but also that we are in fact increasing the correlation between the in situ ground temperature measurement and the one that we retrieved with respect to ERA 5. But then just focus how does it look like when you look at the time series. So here is for a site with a very few water fraction, and what you can see is in black the in situ measurement, in red the ERA5 retrieved ground temperature, and in orange, the results of our model. And as you can see, so we only focus on the winter, of course. We fit much better the temperature, the in-situ temperature that ERA5, even if there are some variation depending on the years and also the time of the season. But it's quite encouraging. And so we were then afterwards for this new study using this method to apply it to as much pixel as possible on the whole Arctic area. So again, we remove all the places with water fraction. So as you can see on the right, there is then quite a few places that are missing now, but we still have far east part of the Russian area, of Alaska as well, and a bit in Canada also. And based on that, we then obtain ground temperature maps, so daily ones, but then we can also compile them either in monthly maps, yearly maps, and so on. So here is just an example. If you compared all the monthly maps of February for all the years for 12 years of the study. And of course, in this database, we see first temporal variation. So as you can see here, when you focus on the temperature distribution for the February months, so there is a consistency in the range of the temperatures that we have, but there are different distributions, meaning that they are happening and having different behaviors depending on the years. And this has to be investigated. All the same with the spatial variations. So here is a quick example. So we made some kind of trends. It's a bit short to call them trends of the ground temperature between 2012 and 2023. On the left for the ground temperature that we retrieve, and on the right is for the air temperature, because we are saying that the air temperature is increasing in the Arctic area, and we want to see what are the consequences to the ground temperature. Knowing that there is in between, of course, this snow layer. And as you can see, there are spatial consistency again, but there are also still some differences, and this has to be explored as well to focus and to better understand how what are the processes that are involved in this determination of ground temperature. And this is why here we still have some ongoing work that we are doing here at FMI. So now we are taking advantage of a polar grid that is now proposed for this SMOS data that will increase the spatial and the temporal coverage that we have in the Arctic area. So now we don't have only daily measurements, but we have orbit measurements. So we have several measurements of ground temperature per day for one site. And we also have like a better spatial coverage of the whole area. So that's increasing the possibility of ground temperature retrieval for the Arctic area. We are also trying to apply this to other satellite missions, such as SMAP that was already introduced by Andreas on Tuesday, for those who were there. Also were operating at L-band. And we hope that this method could also be used for future satellite missions, such as SEAMER, so we can have like a super long time series of ground temperature to monitor the situation. And also we are trying to focus on what is going on and how to include other frequencies in this kind of model like C-band to have a better knowledge of the snowpack, because obviously now we are just assuming and working when the snowpack is dry to ensure this transparency, but it would be nice to extend our model when the snow is a bit more wet and knowing that from other frequency data. Before I told you about the water bodies, and so in this first article we try to find a method to correct these water bodies, so we apply a constant correction for the whole season. So here is quite the similar time plot as we had before for another site when we have like around 20% of water in the field of view of the satellite. And here on top of the previous temperature that was shown, we also have the one retrieved with a dedicated model, including the water body correction. But it's a constant one during the season. And as you can see, it's not working, I mean, it's working quite okay depending on the years, but you have quite a lot of not only inter but intra-annual variations, meaning that it's not always catching very well the early season when the water bodies are not fully frozen but are still freezing, and this is something that we want to focus on. Supposed to have another okay, perfect. And the perspectives of the work, obviously, is to have, so finally, some quite reliable ground temperature measurement that could be included in the study of carbon cycle. As, for example, Mavrovic in 2023 shows that the winter COD fluxes mostly depends on the ground temperature. So knowing this ground temperature below the snowpack would really help us to better define these fluxes. And also nowadays, we are still working on all these temporal and spatial differences that appeared in the database to better know the processes and that are implied by the effect of the local environment, such as like the vegetations, as I told you, they are either shrubs, mosses, lichens, and the consequent snow density or soil type that you can find. And thanks a lot for your attention.
Thank you very much, Juliet. And maybe we have, again, time for a quick question, if somebody have that. Mikko again.
Thank you very much, Juliet. So you obviously have a reason why the tree line is your kind of like boundary, but forestry and forests and their ground temperatures also very interesting. So what's the challenge why it doesn't work there?
So basically now, as you saw, the model is super simple. That this is what we are take advantage of, like just some snow, some ground, and even we say that the snow is transparent. So well, that's quite nice. But we are working now with FMI people very dedicated to the state of the forest and what's going on to the forest to see if we can have like a combined retrievals of either like the forest state or let's say the snow density at the same time as the ground. So this is the basic model, and now we're trying to improve, I mean not to improve, but to add some complexity into it based on the knowledge that we have.
And forests will be included. Excellent. Thank you.
Yeah, thanks.
Thank you very much. Next we have in the program. Change a bit of the perspective to see like what you can analyze from the trafficability side of the Earth observation data.
And now you should hear me better. Great. So good morning, everyone. My name is Joonas Kostela, and I work at the Finnish Metal Institute. I have some colleagues here with me, Mikko Stralendorf, Anni Kröger, Miska Kauppinen, for example, who can maybe answer some questions after the maybe Mikko won't ask the only question this time because he's involved in this. But machine learning for trafficability from Earth observation data is the topic. So why should we be interested in understanding soil moisture? Well, of course, it affects both trafficability and wildfire risk. Also important for deciding routes, for example, when hiking or traveling by vehicles. If the soil is too wet, traverse by foot will be more difficult. Vehicles and, for example, forest machinery can get stuck or damage the ground layer, which the forest owners would most likely like. And if it's too dry, there's of course a higher chance of igniting a wildfire in the area and a higher probability for a wider spread wildfire. And it's difficult to estimate for remote regions, locations, but we have a lot of relevant data available, weather data, Earth observation data, so maybe combining all of this with extreme gradient boosting could be a solution. So as I said, the goal is to predict which soil moisture class a location belongs to. We have used and will use as explanatory or features, inputs for the model, weather variables, for example, precipitation, temperature, evaporation, mostly coming from ERA 5 land at different pressure levels. Some terrain factors, for example, elevation, slope, terrain type, and satellite observations, for example, soil water index values. And of course, in the extreme gradient boosting conditions, define the soil moisture class. So the soil moisture class will be the ground truth, so to say. And on the bottom left-hand side is an example table, very simplified, of the input parameter features and the ground truth observed moisture class. A very simplified explanation on how the extreme gradient boosting works. So it builds many weak decision trees, and each tree improves the errors of the previous ones. And the model is given examples, so for example, weather conditions, terrain factors, satellite observations, and then the ground truth, which is the corresponding soil moisture class. And on the bottom left-hand side is as I said, example table of this. So the result is a model that predicts the soil moisture class when given these environmental conditions. For example, for all of Northern Europe and for past, present, and future conditions, as long as we have the same data available as we used in the model training. And on the bottom right-hand side is a very simplified explanation of the decision trees used in extreme gradient boosting. But what do we actually use as the ground truth? We have this IBA wildfires project where we had this water in your boots or vettä kengässä application, and maybe some of you have seen our stand somewhere or seen a previous presentation. But the idea is that we had two groups, students from the rescue services and the wilderness guides students who went out into the forests, wilderness, and stepped on the soil, lifted their boot, and took a picture of the bottom of the boot and the soil impression. And then they estimated what was the soil moisture like, or terrain moisture, ranging from very dry to extremely wet. And they also gave an estimation on how certain they were about this measurement. And then we used the location and the observation certainty to maybe drop out some of these worse observations from the data set. And from this, we got around 1,700 measurements for mostly northern Finland, Lapland, but also from Norway, Sweden. Some took measurements from the United States, Iceland, for example, when we were presenting this. Mostly Miska Kauppinen was responsible for presenting this system. But on the right-hand side is the observations. On the x-axis is the time. So last year started basically from snow melt, lasting almost to the end of the year. And on the y-axis is the count of measurements per day. So maybe you can see that nearing the end of the year, there was a bit of a rush to get more measurements so that we had enough data for the model training. And of course, the end goal is that, let's say you are standing at one of the green points in the area and you're wondering what's the best route to get to that cyan or blue point. What's the terrain trafficability like? Or maybe you're thinking, can I set a bonfire there? Is the soil moist enough so that there's no risk of wildfire? So from these input features and the so-called ground truth measurements, we have the first version, this ECXN's 15-day soil moisture class forecast product. It has 51 members, so a control run on the bottom left-hand side, plus slightly perturbed versions, resulting in 51 forecasts. The forecast horizon is 15 days into the future, and we also calculate an ensemble mean, which provides more smoother results. And we are also developing a separate past-present model in which we'll use a wider range of different features and also Earth observation data. On the top right-hand side is one of the ensemble members as an example, and on the bottom right-hand side is the ensemble mean calculated from these. So very first results or versions. So from these, we got the B-swarm plots, which show the impact of variables on soil moisture predictions. On the right-hand side, top is for the dry class, and on the bottom is for the wet class. So these are just the top 5 features taken. And each point depicts a time and location from the dataset, and the variables colors depict the variable value. So blue means lower and red higher. So for example, there's the TP or total precipitation. Blue values means less rain and red values more rain in the area of precipitation. And the variables are ranked by influence from top to bottom, and also the SHAP value, how much it impacted the model output. And for example, in both dry conditions and wet conditions, the deeper moisture, or deeper soil layer moisture was the most influential feature. Also surface runoff, for example, total precipitation have high influence on the model output. And some very first results, so ranging from very dry to very wet classes. You can see the precision recall and F1 values, especially the F1 value gives information on how well the model performed, and we can see that it has some issues, or it's struggling to predict the extreme cases, very dry and very wet, for example. But it also has the lowest support, so lowest cases end up in this. So this is a limiting factor which we need to look into more in the future. So for example, most of the observations land in the dry and moist classes, and they also perform the best in this case. So what's next? Well, as I said previously, we are creating this past and present model, which uses a broader range of explanatory variables, for example, Sentinel-1 and 2 data. And as I just said, the first version has some difficulties predicting extreme conditions. So we are going to improve it by adding more variables, for example, environmental condition data, and scale the number of observations in order to better capture extreme conditions and do some weighting on the classes. And the end goal is to provide the end user in an easy to understand format, so that's why we are using classes instead of, for example, percentage. Information on what are the current soil moisture conditions or trafficability, where they are and in the surrounding area, and how they will change in the next few days. And as I also said in the beginning of the presentation, soil moisture is very important factor for wildfire, fire ignition probability, and for example, fire spread modeling. So we'll also look into how to maybe use these results in that. On the upper right-hand side is a picture from Sentinel-1, and on the bottom right-hand side is an example image of a fire spread modeling result from the Kalajoki fire in Finland, where we saw that the soil moisture estimation was a difficulty for the model. So maybe we can fix something like this using these results. Thank you. Questions, comments?
Thank you, Jonas, and we have again time for a few questions. So.
Thanks for the presentation. I was wondering, so you show that your model is kind of has some difficulties for extreme case, so very dry or very wet. Did you consider the strategy of training only for dry case when you are looking for ignition scenarios, and only for wet case when you are looking for very wet scenarios? And does it improve the models when you are looking only at very dry and very wet case?
Okay, great question and good point. I think this is something we could look into in the future. Good point.
Other questions? No? Okay. Oh, there's one in the back. So.
Thanks. Very nice presentation. I was wondering if you have considered these satellite products which have the soil moisture. Of course, the resolutions are perhaps not what you're looking for, but still.
So we are using, I think Anni can maybe comment on this, but we are currently using the soil water index Copernicus product. So yes, we are currently using that in the model training. But maybe Anni can say a couple of words.
Yeah, so as Jonas said, we are using the soil water index layer 2 at the moment as one of the features in the training. And then we have made in an earlier project this similar forecast for it with machine learning, so we can use that as an input in the, if we want to predict the 15-day forecast. But at the moment, in the first version of the model, we are using the climatology that we have determined from the observations. I see Mikko maybe wants to comment something. And we are adding also more satellite products there too.
Yeah, I quickly just say, so we are using this model to do forecast in the future. So the issue with Earth observation in this part is, of course, that we don't have the Sentinel-1 data of it next week. So that's why we have two different models. We try to make another model where we will use a lot of Earth observation data just to tell what's the situation at the moment. And that we try at higher resolution, but now it was easier, we have all the data ready to also make a forecast model to have a prediction for the next week.
Thank you. So very interesting topic, and I think there's a lot of applications for this as well. Next, maybe one more applause to Jonas. Next, we have in program Timo Pyhälahti will be touching a topic that was already partially touched in a couple of presentations, how to get the stuff from the field.
Yes, good morning to everybody. I'm Timo Pyhälahti from the Finnish Environment Institute, Syke, and I'm happy to stand in between you and the coffee because surprisingly I might have actually something interesting to tell you, a bit of an announcement. So, but first some repetitions from the earlier years that you might be already familiar with about the crowdsourcing. What we are doing in Syke is to actually integrate different systems for crowdsourcing, either by ourselves or perhaps copies for the data to be imported from the other systems and for mimicking the other sampling of the data. For example, these wetness things that were just presented. We have an API for these things so that we can actually efficiently generate interfaces for inputting and defining the data to be acquired and working with it with Earth observation data and combining it and also making structures for the monitoring and gathering of the data, because as you see from the earlier last presentation, there were a lot of observations somewhere, but a lack of observations somewhere else, and we cannot actually guarantee that we are actually getting a stream of data as we need it. Basically, we have a system for the software developers to actually attach to our platform of information. And that's what we have been doing also in our Syke systems, either from getting the data from the people who are interested in citizen science on observing the nature as in Järviviki, or as being informed about the nature as in vesi.fi or waterinfo.fi. And we have this Tarkka Sykefi system, you might be familiar with it, and for public display of satellite images. There we have actually two systems. There's currently for two different services, we have this HISP, which is highlighting features of interest in the satellite images, and these are actually gathered also as crowdsourced data from the users of the system, which are common citizens, but also, and perhaps more importantly, also the officials of the different environmental administration, the national or in municipal levels, and other professionals. So it's not just common people who are actually participating in working with this thing. This is the same approach as done with the monitoring of the cyanobacteria bloom, as you see on the right side, to actually map where the locations which lakes are actually filled with this algae bloom stuff. They are gathered not only by common people, but also trained volunteers and by people who are actually working in the different municipalities and so on. So there is a mixed mixture of different inputs. So actually on the right hand side, on the ice example, you see that we are actually planning to have the capability of launching systems for gathering the data also from the Tarkka system, so that we can actually get these descriptions from on site and to compare with the corresponding data from the satellite images. And we have structured information being gathered, so we can actually make statistics and models about these things if there's enough data. And we have also this mobile application platform. It is easy to actually mass produce different systems for monitoring these things. One thing is still, for those with the sharpest eyes, actually notice there in the bottom there's a small box that you can click that this phenomenon that I'm seeing in the satellite image, it's actually worth monitoring for. This is important for the next things I'm going to be saying, but first a few things about this application. Well, if you tick this box in the middle, you are able to send the on-site observation of the ice cover or whatever is the topic is that you are observing the nature. But the big question is how to actually make people to do this thing, how to gather and motivate people to participate. Well, survival is a good way of motivation. If you look closely, sorry for the small fonts, but and sorry for the Finnish texts, but there in the below, there's the announcer is on the left side, and on the right side, it's an application for the reindeer herders, for them to report on the situation of the snow cover related troubles for the survival of the reindeer herds and so on. So this is a good motivator, but there's also other types of motivating people. You could actually assign social status and membership of a group for people who are actually being trained and capable of doing more things, to give them more power on actually commenting and rejecting data and inputs from others, and to control how the thing should be run. So power is a good motivator too. So what actually happens is that in the left side, you see the common people who are actually able to submit data, and common reindeer herder people who can be actually identified by the different means. But on the right hand side, we have a person who has been assigned another API key for our system, basically, which means that they are actually also being added in our systems to different user groups, allowed to do different things. For example, to check for the people the comments that to comment with more authority on the data that people have been submitting, and to approve the data. This is work under process, but this is another top thing that is then allowed for them from this generic
user interface. There's different kind of things that they can do. They can, for example, set these sites for those people to monitor. As you remember from the Tarkka, if there's a cross in that box, somebody has noticed something, and those ones with the authority can actually set that, okay, here we are going to be setting a monitoring site for these kind of things. There was an earlier demonstration of this thing that we could actually sort of show the people how important it would be to do these things and to communicate with them with different signs on the map. But this is still not a really great motivator either. To have structured things to be done, that there's a system, so that there's a site in which things are expected to happen in certain places. There could be local commitment from people, and so we could actually first set the monitoring location to be monitored, to set what should be done there. It could be also something else than monitoring, for example, tasks related to snow cover, for example, or cleaning the roads or whatnot, but basically small tasks to be completed, and a system of saying what actually triggers these tasks. Perhaps a person with more authority telling you things to do or something like that, or there could be a system that if you are actually doing something, you are getting score points, a gamification approach, very nice, or perhaps there could be a system in which you are actually tasked to do these kind of things that you would be actually asked to validate data and create something that is valuable in this sense. Okay, that is a motivator too, but we are perhaps still lacking something. There's change that if you are asking somebody to do constantly something, you are actually never emphasizing when to do things. So we have developed this system of monitoring interest to say how important it would be to do something at a certain location. And then after this triggering, there could be this kind of validation time, like for the satellite images, in which the data would be more valuable. And there would be a similarity time where the data would be less valuable if it cannot anymore be compared with the data. And there could be a reobservation time to actually get time series, so that if an observation at that time triggers a new sequence of monitoring, you could get actually weekly things and so on. And this technology has capabilities for monitoring, but we are still missing something. And the thing with this one is that actually what we have been talking about so far is technology. And these things have been there for a few years. But what we have been actually doing now and testing is this procurement, so that there could be money as a motivator for different organizations to organize the people to crowdsource. And the people who are doing fancier web pages and more nice looking mobile applications could be actually doing their things to either to set up monitoring agreements, to do the observations, and then finally to validate and check what the data is, because there's always the question if the crowdsourced data can be trusted. So now we have an announcement to make. There's 3 companies involved in testing and looking into this platform for this kind of monetary motivation for these things. It's like what is done in Finland with the empty bottles. You are getting small payments for doing certain things, like returning the bottle or getting the data, and we are setting up systems so that we are getting enough, but not too much data on certain locations, enough and not too little data from other less observed locations. And we are currently testing this, gathering the data phase, this middle phase here. And the idea is that we could have procuring organizations which are actually contacting the persons who are actually doing the spreading of this different kind of funding. This dark green is the public funds, and the other colors are some others like non-governmental organization funding and external funding from union or something like that. And the people would be actually managed by those companies who are actually professional in social media and for motivating things and so on. And they could be actually gathering ground funding for this thing in the future and to work with different kind of organizations which would actually organize the local activities. And this is something that could be actually procured by the public organizations or the research projects. Please gather us reference data, and there would be a clear system for us to do this thing. And of course, there's a lot of legal stuff that needs to be taken care of. I will not go into details because I'm running out of time for these things, but there's actually a system also to make sure that the money doesn't run out in the middle of the things, and money doesn't stop when the project is over. And the key thing here would be that we could actually even switch the money from public funding to completely private and common funding. And there's methods also for actually making the payments for the last version so that we could actually assess the value of gathered data later on. And the key idea is that we could actually have different groups to actually match and validate each other's data for the quality, and another group to test for the if this was done actually properly. But my key message is that you could have social media for the spatial data superhood and crowdsourcer, which was recently awarded for this kind of micropayments, and City Nomady, who is well known for creating these kind of web user interfaces for different kinds of crowdsourcing to actually tap on the data systems that we are actually defining for different research projects. Thank you.
Thank you very much. I think this is very, very important topic. Some of the stuff went so fast I couldn't read it, so maybe you have questions also to Timo.
Thank you for the presentation. It was very interesting. I was wondering, was the idea to have a separate app for each scientist project that needs data, or to have a common app that kind of shares all of it?
Yeah, we have noticed that there's too many apps around, so having an app for each and every questionnaire is a bad idea. The PVA app that I just showed you is a generic one to actually combine different questionnaires to a single set. But the different people will be interested in the same topics, so it is actually designed so that we can actually pick the questionnaires for submitting the observations for the different sort of target groups. As you saw for the reindeer herders, there's a specific one which actually includes stuff on ice cover, reindeer stuff, snow, and so on. And even the questions are actually standardized in the platform so that we can have the same sets of classifications in different applications.
Thank you. Will the app also be like a place where you can find out about projects that you don't know about? Say you haven't heard about the reindeer project. Will it be somewhere where you can see that, oh, there is a project like this where I can help out?
Well, we are actually focusing on gathering the data itself. So there will be hashtags and so on about the projects, but it's not an advertisement program for the projects. It's intended for long-term monitoring of things and combining different and joining different projects together.
Thank you.
Yeah, thank you for your presentation. I was thinking it could be also something very cool for us for avalanches and so, but then comes my question. Do you have any mechanism in place, or is maybe something that didn't occur to you, to prevent people from putting themselves in danger to get some data? Because if you have gamification with points and at some point you can benefit from it, people may do crazy stuff to have more points.
Yes. Well, it's a free country and people are allowed to put themselves into danger. But of course, as an official organization in Finland, we are always warning people and so on, but there's only a certain kind of limitation. This is, for example, for these monitoring sites, the decision on where to put them and decisions to actually re-put them to somewhere else is a key issue on this one. And actually I was telling how to actually, in such short time I could not show you the method of pinpointing how people are instructed, but one of the instructions is to keep away from this location and not to make the measurements.
Mm-hmm. I might also comment that one of those mentioned companies organized local data gathering in the area I live in. They used geofencing for blocking, like don't go to the tramways and train tracks and highways. So they were geofenced, so you are not even able to put the point there. So that will prevent people from at least the worst danger areas.
Yeah.
So.
Perhaps I can add a bit to my speech that we are doing the platform, and then there are the applications by these future providers and testers. They have just started, so they don't have a big raster yet on there's just technology testing and so on. But the key is that their applications and the things that they are doing is the thing that the people actually see, and we are there in the background to integrate all these things together, and also for these companies to actually provide a place for long time storage of the data so that it is actually available, and there's the other aspects of motivation so that it is actually worthwhile to gather the data because it's kept somewhere and it's actually a part of something bigger than just one app project.
Thank you. Maybe one more applause to Timo. And I can still see all the speakers, so you can approach them. And now it's time for the coffee in the program, but let's continue the discussion.
Welcome, and let's show a warm welcome to Goats and Benze from Stratospace. Everyone. So this is going to be, you can speak into this, or if you want this. Yes. Okay. Okay, could you hear me? Everything's okay? Bit closer, okay. Now, good morning everyone. I'm Bence Goatsan, founder of Stratospace, and I hope you will not run off as soon as you realize that we are not working with satellites. I'm working with high altitude balloons for the last more than a decade, and I believe stratosphere is the new frontier for Earth observation, communication, and science. With Stratospace, we are building high-altitude balloon platforms to get an affordable solution for research groups and developers to utilize the stratosphere. But there's the question, why balloons? Why would someone who is capable of building a satellite and launching and operating it would invest in balloons? Well, it's cheap, it's quick, and it's easy. Launching a balloon is 100 times less than launching a satellite, and this is only the launch cost. Building the satellite would get its own cost, since they need special components that withstand radiation, vibration, and vacuum. For the stratosphere, you can use components off the shelf in automotive sector, and this would be just fine and keep the production cost low. And don't forget, balloons can be reusable, so they can perform many missions for one building cost. Building a satellite, a small satellite, is 1 or 2 years still. Building a larger satellite is much more. So if you take the current technological advancement rate, by the time a satellite gets into orbit, usually the technology is quite outdated. While you can launch a balloon in 6 months. This is from idea to deployment. You can use the latest technology. You can update your technology from flight to flight, so you can test, validate, and iterate in a very short period. To launch a satellite, you will need a launch vehicle, a launch pad, infrastructure, specially trained team. You have to work with heavy machinery, dangerous chemicals, and still rocket launches are dangerous business. While if you want to launch a balloon, you just need a suitable field. For larger balloons, it's better to be an airfield, but you can launch a small balloon from a football field. Our platform is so small, we can launch it from the back of a pickup truck, and we've got a 2-man launch team, so virtually we can launch from anywhere. Balloons, compared to other means of Earth observation, have their advantages. For example, compared to drones, balloons can cover a larger area and operate for a longer time. And looking at satellites, balloons are more flexible, cheaper. They can stay over the designated area for a longer period, while satellites just rush over the fields. And also, if you take a camera from a satellite and put it on a balloon, it will be closer to the ground, or closer to the surface, so it will provide a better resolution as well. I cannot say, however, that balloons are superior to all of these Earth observation vessels. They have their disadvantages as well, and I always say they are not competitors for a satellite, but they are a complementary service to enhance data resolution for a designated area. And when I'm talking about balloons, usually 2 pictures come into people's mind. One is this one.
which is a latex weather balloon, usually associated with university and high school projects or hobbies. And this is us launching our very first balloon more than 10 years ago, and we were still university students or hobbyists back then. Another picture is this, which is a large foil balloon. It could be the size of a football field, and it's usually launched by larger organization. This one is a Bexus balloon launched by the Swedish Space Corporation. And if you check this red balloon, it's about the size of this white balloon we are struggling on another picture, so you can feel the size difference between the two. And this is us again with our latest improvement, which is a small foil balloon, and this is our vision to provide the facilities of a large balloon to smaller players, to smaller payloads in an affordable way. So we are aiming for long duration balloon flights, and for that we developed the light balloon platform and services around it. Our avionics unit is 700 grams. It have the live tracking for the balloon, two-way radio communication for telecommand and telemetry, and it has altitude control as well. Also some automated features to operate the payloads and keep the balloon on track. We have solar panels for power, so this helps us get long duration flights. And also we have a communication which doesn't require line of sight, so we can go very far from the launch site or the operators. We can take 2.5 kilograms of payload with this light platform up to 30 kilometers to the stratosphere. And with this balloon category, you can organize a launch in a very short notice. We can prepare the platform also in a very short time, even shorter time than the notice has to be done. And we can launch from Hungary almost any time of the year, and some other European countries as well. We do the balloon preparation, the launch, the operation, we recover the payloads, so the customers only need to focus on their experiment. We can also provide just the launch service, so complete payloads who have everything they need. We just do the launch, and then the operation is the responsibility of the partners. And this is our balloon platform, AVO. We use our proprietary zero pressure balloon for loitering and floating periods. We also have the ballast dispenser in the avionics unit, which helps us keep the altitude at the same level or change it if it needed. And in the, it has a two gondola system, so the payload goes in a different gondola, and it could be basically anything. So when we designed the platform, we had in mind Earth observation, but we have to be flexible enough so we can support in situ experiments, technological demonstration for spacecraft components and subsystems. We already did some flights in this domain. And we recently built a rideshare gondola, which can accommodate several smaller payloads, and they can fly to the stratosphere at once, so it would keep the launch cost even lower. I brought you a case study, how these light platforms can be used, and I choose a hot topic which is more of a problem from summer to summer in Europe. It's forest fires. So to contain the flames, firefighters need live information where the fire is, and they can prepare their operations. With a balloon, we can fly over the fire and provide good enough resolution images almost real time, and the firefighters get them at their hands anytime. But data is not enough if it couldn't be communicated. And unfortunately, forest fires happen in remote locations where communication infrastructure is not present or already damaged. In this case, balloons can act as communication systems on the site, either provide LTE or other network coverage, or act as a communication relay between handheld devices, satellites, and control centers. To achieve this operation, the best is use 1 or 2 balloons that could circulate over the area. We put very high hopes in this method. We really wanted to work because we've seen it work in North America, in the Southern Hemisphere. But we are in Europe, and we are developing for Europe. And Europe is a bit different in climate. So our data shows that this kind of operation, when we stay over a smaller area, is only available for limited times of the year in our continent. But we are now doing a year-long experiment with a large number of picoballoon flights to determine wind map and see how it really is and how the data gets closer to what we see right now. So if we don't have loitering, we couldn't do the station keeping what to do. So our balloon platform is small enough to build several identical ones. And our launch team is a 2-man team in a pickup truck, so we are mobile. And the solution is to launch multiple balloons to cover the area. And we can travel from launch site to launch site as the wind's direction change. So we can always keep 1 or 2 balloons over the forest fire or over the operational area. And as soon as the balloon leaves the useful area, they can force to land. And after recovery, they are ready to fly in a very short period. Our next step is extend our payload capacity up to 20-30 kilograms and build the infrastructure to do this kind of launches. With this kind of platform, we can fly a 6-unit CubeSat all together as it is complete. But this is not a technological challenge. It's more likely a legal challenge, so we have to get all the permits to launch heavy class balloon in Hungary, and this would take time. Until then, we will continue to provide the 2.5 kilogram payload services. And in any case, you have some payload which is need flight opportunity, or you need consultancy with your stratospheric project, just contact us either on the internet or find me after the session. I will be here today still, tomorrow not, but you can find me. Thank you.
So thank you, Mr. Gozan, for your amazing talk. Anyone have questions? Right there.
Thank you, very interesting. Question about getting permission to flights. So in other words, air traffic is regulated and you have to have a flight plan. How do you manage that with balloons and doing these kind of operations?
So we are operating in the light balloon class, which only requires notice towards the flight associations. They then notify the towers and the planes that there will be balloon launch, but this is so small category, it is not a threat to air traffic right now. With heavier class, you would have to maintain more regulations, and that would be the next step for us.
Are you carrying the biggest payload for that category of flight regulations?
Yes, so we determine the payload size to fit in this category.
Thank you for the talk. To what extent do you control which way your balloon is carried by the wind and where it will land?
We can change altitude, and above 20 kilometers, there are usually very distinguished layers of wind, and with this you can, in theory, you can change direction as the winds blew other directions, but over Europe it tends to blow to one direction, and you can control the speed of the travel mainly by controlling the altitude. So get into different air air layers, you can get different winds.
Thank you for the presentation. In terms of the controlling and picking up the payload afterwards, do you have any technology that you make use of for like predicting where the balloon is going to land beforehand, or is it just you're using communication with the balloon to see where it lands and then you go to pick it up afterwards?
We do predictions beforehand. We use our own calculations, and then from that calculations we use the data for open source predictors, and this way we manage to have a very good prediction, 1 kilometer accuracy. But now we started to work on our own system where we feed back the live data we get from the balloon and make more precise predictions using that and the forecast as well.
Would that be like a real-time prediction?
Yes, that's the goal, to have a real-time prediction.
I see. Thank you.
All right, we have time for one last question.
Exactly, yes. One sec.
A quick one, please.
So what is the usual or the maximum flight time of these balloons?
So, see, we are operating in Hungary. We still have to stay inside the border. We're working on to get much further, but the complete flight time could be 6 to 24 hours. Or even more. That's our prediction, to have a couple of days of flight with this technology. But currently our longest flight was 2 hours over 20 kilometers. Of course there was the landing and ascent, which made it around 5 hours of total flight.
All right, let's thank the presenter again.
Thank you.
My name is Ville Lundén from Aalto University. I'm happy to take over the chairing of the rest of this session. And now for the next presentation, I would like to welcome Juha Kainulainen, who will be talking to us about the CIMR air instrument, an airborne multi-frequency radiometer system. The floor is yours.
Okay. I guess everyone can hear me. Back row, raise one hand if you can hear me, and 2 hands if you can't. Okay, good. Okay, here in the beginning, as a little prologue, I would like to take you to a time travel. I want to travel in time with you to 3 specific moments in time and place, which I actually came up last evening when I was thinking what and why I and you are doing here in the first place. And first I take you 400 years back in time to Italy to meet Galileo Galilei. He taught us essentially that the world is understood best if you measure it. And to measure it, you need instruments to measure, sensors, if you wish, like a telescope. And by this simple idea, he built the whole foundation of the measurement or observation, instrument-based scientific method that we all follow here today. So was followed by Mr. Robert Dicke in less than 100 years ago, when he developed a new type of microwave passive sensor called Dicke radiometer. This was a new technology that improved the existing technology significantly, so that even weak signals of microwave radiation can be measured. And indeed, a bit later, astronomers Penzias and Wilson used a nice telescope and a Dicke radiometer to measure the cosmic background radiation, which is the foundation of our current understanding of the universe. So these two moments in time definitely created a quantum leap in our instrument-based science we are doing. Perhaps the third quantum leap happened in 2007 when our company HARP Technologies was established. Well, time will show if it was a leap in what direction. But anyway, our company has been there almost 20 years providing contract-based R&D services in millimeter and microwave technologies. We are located nicely here in Espoo. We are a small company of 17 employees at the moment. Get more information from the booth. But briefly, few examples on the slides. We have done microwave instruments which mainly are targeting to scientific applications. We built tower-based radar systems, airborne instruments, some satellite-borne instruments, EM simulations, and so on. This takes us to my keywords and contents of today. Two first bullets I told you already. Science needs sensors and microwave sensors, which HARP Technologies can build. Then I take you to two future sensors. One is ESA's SIMR mission, and the other one is SIMR Air system. European Space Agency's SIMR mission is part of Copernicus program, which is ESA's huge Earth observation satellite fleet. SIMR Air is ESA's first high-resolution, passive, low-microwave conical scanner mission, having probably Dicke radiometers or similar. It makes radiometry at L, C, X, K, and Ka bands, so from 1 gigahertz up to 36 gigahertz. The main applications being sea surface temperature and cryospheric parameters. There will be two identical and consecutive satellite missions launched, aimed at the moment in 29 and 35 approximately, covering a time period of 10, 15 or 20 years from the launch. Now, SIMR Air instrument is an airborne demonstrator or reference instrument for the space mission. European Space Agency has used airborne instruments to support many satellite missions. They are used to collect data for geophysical retrieval in more controlled environment that can be done from a satellite, and also to validate satellite measurements. And for this European Space Agency SIMR mission, HARP is developing, together with Finnish Meteorological Institute and Technical University from Denmark, an airborne reference instrument which has characteristic and main specifications very similar to those of the satellite instrument. Here are some of the key requirements and specifications of the SIMR Air instrument. As said, we are operating on 5 frequency bands from the L band up to 36 gigahertz. We are making fully polarized measurements, so retrieving so-called all 4 Stokes or modified Stokes parameters. We operate in bandwidths of few hundred megahertzes, and incidence angle shall be 55 degrees, often used in remote sensing. We have also ambitious requirements for the accuracy of the instrument, below 1 Kelvin instability and accuracy. Operationally, this should be a modular instrument installed in a twin otter type of an aircraft, which is a typical unpressurized aircraft used in many climate studies. It can fly up to 300 meter altitude and fly close to 6 hours in duration. system shall be operable in different temperatures, and in addition to these radiometers, it shall have a visual camera, infrared camera, and an infrared thermometer for sky radiation measurements. It provides, the main data product is antenna temperature, so the power collected by the antenna, but it also provides some scientific products like sea surface temperature and sea ice concentration. And our solution for the instrument is shown here nicely on the figure, illustrated in the side door of one Twin Otter aircraft. It's a side-looking radiometer system with 5 independent radiometers with a compartment for visual and infrared camera and other cameras, and an independent navigation unit to provide position and time for the instrument. It is planned to be installed in 2 aircrafts at the moment, one in Iceland and one in Canada. And the airworthiness processes for these 2 aircrafts are ongoing. Here's a little detail where you see the 5 antennas from the side door and the camera compartment. Then I go into some technical highlights of the instrument. This is another view to the electrical structure of the instrument, showing basically the 5 radiometer units which are connected to the central CPU, the cameras, and the navigation unit. The instrument can operate without a single, with just a single one of these, or combine all together, everything together, operated with a single operator. This is how it looks physically. The radiometer boxes are included in 2 racks, height of 1.5 meter approximately. One consists the largest antenna, which is the L-band antenna, and another rack, the 4 remaining radiometer units. That's the central computer unit there. One technical highlight of the instrument are custom-made antennas for the purpose for extremely good performance. We have 5 antennas in the system which have extremely high main beam efficiency, so low side lobe and high ohmic efficiencies, meaning good, and also high cross-polarization isolation. On the largest antennas, they are implemented as horn antennas using spline technology, meaning that there's a certain curvature of the antenna, making or shaping the main beam and the side lobes as we wish. Corrugated horns are used at higher frequencies. This is a detail how a single radiometer unit looks like. Basically, the antenna is enclosed in an antenna enclosure, and the electronics is behind it in a thermally insulated and controlled radiometer box. Then some electronics behind the box. Temperature stabilization is a key parameter in radiometers, so that has been paid attention here. The heart of the radiometer is, of course, its receiver, and here we use so-called balanced Dicke radiometers, thanks to Robert again from the first slide, which are kind of enhanced Dicke radiometers. It uses special techniques to further enhance the performance of traditional Dicke radiometer by changing the power measurement into a measurement of time, which, thanks to modern digital technologies, can be very accurately controlled and measured. Otherwise, they are super heterodyne receivers, including internal calibration and so on. No more about that. In practice, it looks like this. It consists of modular waveguide parts seen on the left side. The antenna is attached to the waveguides on the left side, and then we have a set of waveguide components and modular components, and then the intermediate frequency part, or mixing and intermediate frequency part, is on planar structure seen on the right side. Then the data is taken to the state-of-the-art RF system on chip, which applies different digital techniques to detect the power level and control the noise injection functionality. Also, interference detection based on frequency subbanding is implemented in this digital signal processing unit. That's some technical highlights in the end. Currently, the radiometer system is in bits and pieces on our laboratory. We are integrating it and testing it at the moment. And the plan is to participate it with the first scientific campaign in Canada in April this year. So pretty soon in the future. Certification to these two aircraft, which I mentioned in the beginning, is ongoing. And when ready, SIMR Air instrument is ready for 10-year service to support the SIMR mission. As a conclusion, I repeat what I had in the beginning. Remember that science needs sensors. You can get them from HARP Technologies. And ESA is making state-of-the-art sensors to the satellite. SIMR is one of them, and SIMR Air system is to accompany that satellite. That's all. Meet us at the booth area and discuss more of this, or if you need sensors for your science. Thank you.
Thank you very much for this interesting presentation and introducing us to your nice instrument. Do we have any questions from the audience?
Thank you for the description of your sensor system. Because I'm not familiar, what are the practical use cases of this sensor? What would you be looking for with these sensors, and how could you apply that for practical situations?
Practical applications of this particular sensor you are asking. So it's typically used by scientists. The main applications are, as far as I understand, I'm not scientist, I'm engineer, are cryospheric applications. From the signal that this instrument measures, scientists can calculate, for example, snow parameters, temperature of sea, depth of ice, this kind of parameters, but really you have to ask from scientists.
Okay, thank you. You mentioned in some slide that you're also going to provide sea ice concentration. Do you already have decided what or which algorithm you are going to use for the sea ice concentration?
Yes, that's pretty much decided, and you have to ask your colleague Marko Mäkynen about that. He can tell, okay. Or Juha Lemmetyinen, he can tell the exact algorithm.
Well, we are using algorithms that are used for satellites also, some couple of typical algorithms.
Thanks.
Any further questions? If not, then let's thank the speaker again.
Thank you.
And the next up, it's my pleasure to introduce you to Lorenzo Regalbuto, who will come and talk to you about the Kuvaspace Hyperfield constellation.
Good morning, everyone. My name is Lorenzo Regalbuto, and today I will show you what we are building at Kuvaspace and why we are doing it. At Kuvaspace, we build satellites for Earth observation using hyperspectral cameras. We like hyperspectral not because it's better than other technologies, but other technologies are just not able to fill a gap in the image information that only hyperspectral can do. Here is a brief example that shows how hyperspectral can collect the spectral signature of the observed objects and identify the materials. In this case, we can distinguish between similar military vehicles for a defense application. The way we want to deliver hyperspectral insights consists of an innovative architecture made of two main segments, a space segment of almost 100 satellites and an AI capability able to provide smart, actionable, and near real-time information to the users. Today, I will talk about the satellite side of our company. Currently, we have two 6U CubeSats in orbit, Hyperfield 1A and Hyperfield 1B. The next generation satellite will be launched by the end of this year, and the name is very creative with respect to the previous one, Hyperfield 2. Hyperfield 2 represents the core design of our future constellation. We aim to deploy almost 100 satellites by 2030 to provide sub-daily revisit time. The revisit time is the time interval between two successive observations over the same area. So let's say that in 2030, over Helsinki, for example, we can take more than one picture per day. And these are only some of the more than 20,000 beautiful pictures that we have collected so far with Hyperfield 1. If you also want one of them for your bedroom wall, you can visit our website. So let's talk about the protagonist of this presentation, Hyperfield 2. It is a microsatellite of 75 kilograms with deployable solar panels, electric propulsion, 3 hyperspectral cameras, plus one very high-resolution RGB camera, with onboard devices that are not common to be found in space, like a GPU, an AIS receiver, and an inter-satellite transceiver. And I will try to go through all these points to get a better understanding of our satellite. First of all, Hyperfield 2 will be launched into space with the Falcon 9 of SpaceX in a sun-synchronous orbit, so over 500 kilometers from our heads. After the deployment, the satellite will use the propulsion to accelerate the descent phase until the operational altitude is reached. And when the operational altitude of 380 kilometers is reached, the satellite will continue to operate with propulsion subsystem against the atmospheric drag. Indeed, otherwise the satellite will fall in lower and lower orbits because atmospheric drag is not negligible at that altitude. And this is what actually will happen when the propellant runs out, avoiding any long-term trash and debris in space. The propellant we use is xenon, and it is used by a Hall effect thruster. A Hall effect thruster is a propulsion subsystem that generates thrust by ionizing the propellant and accelerating it via electric and magnetic field. This topic will require an additional presentation to be properly explained, but it's nice to notice what is the visible effect of a Hall effect thruster. It looks like a tiny northern light generated by engineered ion accelerators. The required power, as you can see from the table, is quite high, but our power subsystem is able to support much higher power requirements. It consists of an extensive architecture of 2 solar arrays, each one with 2 solar panels, with additional solar cells on one side of the satellite. And the most power-hungry device is a GPU that is necessary to run AI models, not only for in-orbit image processing, but also for cloud detection and image compression, which are extremely useful to avoid any waste of data in orbit and accelerate the downlink of the data. The ADCS, Attitude Determination and Control System, is the core of any spacecraft, and it is responsible of maneuvering and rotating the satellite around itself. On Hyperfield 2, it consists of a group of sensors with 3 sun sensors and 1 single sun tracker for very accurate attitude determination, and a group of actuators, so the component that actually provides the torque. It consists of a group of 3 magnet torquers and 4 reaction wheels. Regarding the communication architecture, it's important to say at the beginning that typically Lower frequencies are less sensitive to the weather conditions and so more reliable, while higher frequencies allow for a faster data rate. This is why on Hyperfield 2 we have a S-band link for the downlink and uplink of telemetry and commands, so from the ground station to the satellite and vice versa, and a X-band link for the downlink of the payload data, which is quite heavy, up to 400 megabits per second. But what if Hyperfield 2 is out of the range of any ground station and we need to communicate with the satellite in a specific moment? We can rely on a inter-satellite architecture, a cross-link architecture, with relay satellites on higher orbits to exchange commands, telemetry, and AIS messages at any time. AIS stands for Automatic Identification System, and it is the communication architecture used by ships and coastal stations to exchange necessary information like position and velocity of the ships. And this is a terrestrial system, but it is possible to intercept these ship messages also from space, and this is why we have an AIS receiver on Hyperfield 2. But the hidden value of having an AIS receiver stands on two main applications. First, we can collect a global spectral vessel library, and secondly, it is important for detecting dark vessels that turn off the AIS to perform illegal activities, and comparing with the data we collect with our optical payloads, it is possible to send the alerts in near real time to the users thanks to the inter-satellite link. So let's now talk about the most precious gas on board our satellite, 3 hyperspectral payloads with exceptional performance, with the availability also of multiple points, and this allows for the increase of the SNR to very, very high values. The SNR signal to noise ratio is the ratio between the light signal coming to the camera and the undesired image noise. And in other words, high SNR means better image quality. The 3 hyperspectral payloads cover the visible, near-infrared, and short-wave infrared regions of the light spectrum with SWOT width of 30 kilometers and ground sampling distance of 15 meters. The SWOT width is the large dimension that a camera can take in one picture, while the ground sampling distance, GSD, is the smallest dimension that a pixel can detect. And in other words, in this case, it means that objects smaller than 15 meters is not possible to distinguish them. But this limitation is overcome on Hyperfield 2 because we can rely on a very high resolution camera with a GSD of 3.6 meters that provides a hyperspectral capability with an actual spatial context. In conclusion, Hyperfield constellation will be populated by almost 100 satellites to provide sub-daily revisit time everywhere on Earth, and on board a GPU, an AIS receiver, and an inter-satellite transceiver to deliver intelligent, actionable, and near real-time data to the users, thanks to a very high resolution hyperspectral capability. Thank you for your attention, and I hope you enjoyed my presentation.
Thank you very much for your enlightening presentation into the technicalities and capabilities of the Hyperfield satellites. Do we have questions?
Yeah, very quick question about because you say you have a GPU.
Yeah.
I don't know how big it is, but how do you plan to cool the GPU? Because it can eat like to, I don't know, 80, 90 degrees. So how do you cool it in space?
Thank you for your question, and it's actually a very good question because having a GPU on board a satellite is actually very challenging because it's not made for space, it's made for Earth applications. And this is the innovative part of our satellite, that we take a component from Earth applications and we made it compliant for space in terms of thermal problems, also radiation problems. And we have, let's say, a passive way to disperse the heat of the GPU. And we have actually analyzed that one, and we are going to qualifying it in the next few months.
Thank you for your great presentation. Really interesting about your spectral sensors. Question about operational limitations. Is the sensor available to work during only daylight hours, or can it work during at night? What are the limitations for weather? And I have a second question related to ship fingerprinting.
Thanks for your question. Unfortunately, no, we cannot overcome this limitation because it's an optical payload. The only new feature we have on the Hyperfield 2 is that when a picture, for example, is very cloudy, with the model of cloud detection in orbit, we can avoid, let's say, the downlink of this data, which takes only time, and it's a waste of data and time, of course.
Thank you. And then with regards to building a library of ships with hyperspectral data, a lot of ships remain the same. So a tanker, the top side of the tanker remains the same, but a cargo ship with containers changes all the time. How do you plan to handle that challenge?
Can you repeat, please, the point of the
So if your satellite's looking down at ships,
yeah,
the top side of a tanker is always the same because there's pipes and it's always the same look on the top side of a ship. If you look at a container ship, there's different containers every time the ship moves. How do you plan to fingerprint a ship that has different containers in view from the satellite?
I honestly cannot answer this question because it's more about data analytics. On our company, we have a satellite side and a data analytics side, as I told you at the beginning of the presentation. And I don't want to give you wrong answers, but at the booth, I'm sure my colleagues can provide you with a proper answer.
Thank you for your talk and for not leaving space debris in the orbit. My question is short. What is the expected lifetime of Hyperfield 2 in the orbit before the propellant runs out?
Thank you for your question. Currently, the lifetime is up to 5 years, but of course it could be less because it depends on the atmosphere, also on the sun levels and several factors. And at the moment, with this amount of propellant, we aim to reach a maximum lifetime of 5 years per satellite.
May I ask also, how much does it cost one satellite?
How like?
What is the cost of this one satellite?
The cost?
Yeah.
Actually, I don't have the cost in my hand, but millions, I would say.
Yes, thank you for interesting talk. I wonder if the AI systems on board select the targets to image and do you need actually ground control to select the areas because of the cloud cover, etc.?
So most of the work is done by operators on the ground. So we select the targets based on the requirements of the users and the customers, because of course the first requirement comes from a user. So it's not the satellite that decides to take picture over a specific point. And as for the cloud, you said cloud, right? We also, of course, can rely on the predictions of the weather to understand if it's worth it or not.
Yes, so the ground operators actually have the cloud information and select which objects are actually probably visible and then select these things. Thanks.
Yes, exactly.
All right, do we have still time for one short question up in the left row?
Hi. Baldur from Cybernetica. How to get in contact with those guys in your R&D who are writing the specs and testing for these temperature and power demands of the GPU depending on the different tasks that you are planning to put on it.
How to get in contact with, sorry?
How to get in contact with the R&D and discuss this design phase of developing specs for putting AI on space. You mentioned that currently you have not yet gone through it. We are doing something similar exactly now. So I'd like to discuss something.
Yeah, sure. We can discuss it, of course, after the speech, right after it. Yeah. Thanks.
Thank you.
Thanks for your question.
All right. Then let's thank the speaker again.
Thank you.
And thank you to all the speakers of the session and to the audience. This concludes this session for now. And the next presentations will be in the main lecture hall, Kaleva, some keynotes before the lunch.
Hello, good afternoon. So, welcome to this forest remote sensing session, followed by vegetation remote sensing session, which kind of treat similar areas, but we've divided the presentation so that we move from the more general or more specific forest to the more general, which is vegetation. But in Finland, there is always been a strong emphasis on remote sensing of forests as the dominant vegetation cover here. And it's my pleasure to chair you this session together with Eduardo Maeda from University of Helsinki. I am Matti Matus from VTT Technical Research Center of Finland. And there have been some interesting presentations also on vegetation before, like in the hyperspectral sessions 2 days ago, and also in the application sessions, but it's always difficult to draw a line where is where, but we've tried to find 5 very interesting presentations now for this session. And to kick it off, I'll give the floor to Sanna Härkönen from Sitowise about detecting dead trees in, I assume, Finnish forests now.
Okay, hello everyone. So could I also see my presentation there? Well, you can see it here, but I can start. Okay. So my presentation is about detecting dead trees in Finnish forests, and this work is based on a project that we had with Finnish Forest Center, and that was innovation project where the goal was first to compare different kind of methodologies and data sources, and then select the one which would be good for real production. And after the project, which ended about a year ago, we then implemented this to production, and since last summer it has been also used in real use cases. So the innovation partnership project was really aiming to real situation. So now you can see that there is this, for example, this newspaper there showing what is already done since last summer. So over 20,000 forest owners have received message about their forests, that there are damages there, and they should go and check what is going on there. And here, just for general overview, what kind of data could be used for this kind of dead tree detection. We were looking before really starting this project that which data sources would be the ones that we want to focus on. And of course, this very high resolution satellite imagery, which is available from commercial data providers, was one of the data sources that we wanted to look at more detailed. But then also these free aerial images that are available from, for example, MML was one of the data sources we were also testing. And then we were also comparing the models which were trained with this high resolution data with those from freely available Sentinel data. And then, of course, you could use this kind of drone data very, very accurate data, and LiDAR data, Sentinel-1 as additional data sources, but we were concentrating on these data sets that are presented in this slide. So Sentinel-2, then three different kind of commercial satellite data sets from SPOT, Maxar, WorldView, and then SkySat. And then we also compared this aerial images from MML, Land Survey of Finland, and tested different kind of models, algorithms. So started with very basic ones with random forest, and then tested also the CNN different versions. UNet was then the one that we ended up with to the final solution. And then the results were validated with validation data that was not used in modeling, and also had some field observations to be used with this analysis. And here are results. So first, starting with this highest resolution, so SkySat and Maxar data sets, where the resolution was around 0.5 meter. This SkySat was tested in quite many different areas in Finland, so 11 test data sets were in our analysis tested, and the accuracy with those varied quite a lot, so from 70% to over 90%. And with this Maxar WorldView, we got really high accuracy then. Of course, there were also some challenges in some of those images, so it was not so easy to use all the images because the quality varied sometimes quite a lot. And then if we look at this not so high resolution data sets that we also looked at, then both with the SPOT and Sentinel-2 tests, the accuracy was about the same, so around 80%. And then the last one, so these freely available aerial images, this was really the best option in our tests. The accuracy with our modeling was over 95%, and then of course with this data, if you have this up-to-date data available and it's freely available, then it's very convenient to use. But the problem or challenge is, of course, that this update cycle in Finland is 3 years, so you get the up-to-date data only for 1/3 of Finland each year. But if we look then at the conclusions, so we have decided that we use this MML aerial images if they are up to date. So that is then the base data, and if for the other regions there is no up-to-date data available, then we utilize commercial satellite data then for those regions. Scalable CNN model was then the final solution that we came up with, and that has been then implemented to our platform where we run the results. And maybe just 2 things which are really like requirements for this kind of production ready modeling process is that the data that we use has a really like stable quality. So the light conditions where it has been captured is about the same, and the quality is also good. So there are no clouds or fog or whatever disturbing the analysis. And here is just the final flow that is now running in the production. So how it works, we are running this AI detection in our servers. Then we deliver it for Finnish Forest Center, and then their Metsään.fi system sends announcement to those forest owners where whose forest have some problems. So there are dead trees there, and the idea is that when we detect these problems early enough, then these bigger damages can be prevented. And now it's really like running there, and next summer we are continuing this analysis when new data is coming. So thank you. If you have questions.
Hello. So thank you very much. Very interesting presentation. So do we have questions from the audience first? Okay. Yes.
Thank you very much. Very interesting presentation. Question, if you are a forest owner, do you need to do something to get this information, or do you get it automatically in this forest center website?
This Metsään.fi, you can at least sign in there and see there this information if there is something wrong. But I think also they should be sending text message. I'm not completely sure how it works.
Yeah, I can confirm. So, because I had that message and I just joined the session to learn how it works in the scene. So they sent, I think, email to me that there is dead trees.
Thank you. Another question?
Hi, Einar Heiner from Koko Forest. We're the other partner in the project, and I'd just like to ask. So you mentioned you've been using these different high-resolution satellite data sets. How have you tackled the challenge with the different sensors and different image qualities? So have you tried do you have a model for different image data? You don't have to answer if you don't want to, but I'm just curious.
Yes, this is a good question, and it is really as I think you also have noticed the same thing, that there was a lot of variation between the different kind of data that were tested in the project. So it really makes challenging to create one model that would work for all.
Okay, so that was actually my question too, would have been that VHR satellite data comes with very different resolution, contrast, quality characteristics. So it takes still more time to build a kind of a universal algorithm, I guess.
Yeah.
Okay, if you have one very, very quick question from the audience, we can still have time to answer. No, thank you, then we will move on.
Thanks a lot, Sana. All right, so the next speaker is Jorge Namorado, coming from Catholic University of Leuven in Belgium. He will talk about detection of commodity-driven deforestation using Sentinel-1. Welcome, Jorge.
it's not working. Okay. Okay, so, well, good afternoon, everyone. My name is Jorge Calderón Enamorado, and I'm a research fellow, junior research fellow in remote sensing at the Tartu Observatory. Today, I'll be presenting my master thesis done within the UC Louvain and Tartu University, titled Automated Detection of Commodity-Driven Forest Loss in Tropical Regions Using Sentinel-1 CISAR data, focusing on supporting EUDR monitoring across multiple land use and land cover types. Okay, so the European Union plays a major role in global deforestation by its consumption of agroforestal commodities. So by the year 2030, it is expected to drive 248,000 of hectares of deforestation annually. So these consumptions these commodities come from timber, coffee, cattle, soybean, palm oil, cacao, and rubber. Now, to address this, the European Union enacted the European Union Deforestation Regulation that aims to stop the introduction of products that are linked to deforestation after the 31st of December of 2020. Now, monitoring all of these things in the tropics still remains a challenge, especially because we have huge cloud covers, and we have also complex fragmented deforestation patterns. So this remains a challenge, including the use of optical satellites. So in this case, the use of Sentinel-1 SAR is favorable because it can operate under any weather conditions and can penetrate heavy cloud coverage. So in this slide, we can see a 2023 annual composite over the Rio Plátano biosphere in Honduras. On the left, we see the SAR image composite, and on the right, we see optical, and we see a clear comparison between its heavily cloud covered, and on the left, it's basically cloud free. So having this said, the objective of this research was to develop an automated quarterly method to detect forest loss linked to 7 tropical commodities using SAR data, supporting monitoring efforts under the 2023 EUDR. Now, besides using Sentinel-1 data, 2020 forest masks were employed. First of all, the global forest cover, tropical moist forests, ESA, ESRI, and other regional datasets, all of these having a 10-meter resolution. Additionally, Planescope imagery with a resolution of 4.77 was employed to validate visually deforestation confirmation and accuracy assessment. So all of these study areas were located in the tropics. 4 of them being in the Americas, 2 in Africa, and 1 in Asia. So going to the Americas, we start with Honduras for coffee. Then we go to Colombia for cattle. Then to Peru for timber. And lastly to Brazil for soybean. Now going to Africa, we go to Côte d'Ivoire for cacao, and to Nigeria for palm oil. And lastly, go to Asia, Cambodia for rubber. So all of these images depict that the structure is really complex, highlighting the difficulty in the monitoring challenge. Now, all of these images were pre-processed using Google Earth Engine, the Sentinel-1 images. So quarterly composites were generated for each study area spanning from 2020 to 2024. And the quarterly composites were considered because it was an optimal balance between data availability and detection sensitivity. So following this, from both polarizations, BH and BV, statistical metrics were extracted. So in this example, we have Cartagena, El Chaira, Colombia, the first quarter, spanning from January to March 2020. So the metrics were minimum, maximum, mean, median, standard deviation, 10th and 19th percentiles. So for this study, the BH minimum metric was selected due to its higher contrast and sensitivity to changes. Now, this methodology relies heavily on the threshold-based difference detection. So in this example, we go to Atalaya, Peru. We have the BH minimum quarter, 12 quarters spanning from October to December 2022, and the 2019 annual baseline. So all of these quarterly images were compared to this annual baseline. And as a result, we see here, all the changes relative to 2019 that are clearly visible. So after this, the distribution of each backscatter image was divided into mainly 5 quantiles. Being the first quantile, the upper limit, served as a threshold. Now these quantiles basically changed depending on the speckle noise sensitivity, backscatter distribution, and empirical testing. So to minimize the threshold variability, a trimmed mean averaging technique was employed. Here, the lowest and the highest 10% of the values were removed, focusing only on this central tendency. Now, this is the threshold for this specific study area, for this polarization as well. So once applied, we see, as a result, we have this binary mask. So once we have this binary mask, 2 processes were followed to enhance it, basically. First, a speckle noise removal with a morphological opening of 2x2, and then an isolated pixel removal of 2 steps. This basically smooths the detection and closes any gaps. Following, this process is done in both polarizations, in the BV and the VH. So once we have them, we basically merge them to enhance reliability. And we can see how both of them complement each other. And lastly, each quarterly merged mask was compared to a cumulative record of past deforestations, ending with this patch detection that corresponds only to the 12th quarter. And here on the left, we see a planetscope image from November 2024, and on the right, we see the overlay of the annual detections from 2020 to 2024. As we can see here, it's a clear progression of forest loss. Now, we need to validate these detections, right? So before validating, we need to select the most appropriate forest mask. Here are the 4 global forest masks that were used. And even though they are all similar, each one has distinct differences. And selecting the best one is really crucial to detect these changes. So once this S3 2020 was selected for Peru, once we have it, the 2020 detections were filtered out and remaining only 2021 to 2024. And as a small conclusion here, once we have this already validated, we analyze the data for spatiotemporal patterns of forest loss and degradation. Here, most of the events occur during the dry season, matching with land conversion activities associated with each commodity. Following, regarding the forest mask validation, the best mask that was tested was S3 2020, and as an overall, we can say that all of these global masks often lacked local specificity, highlighting the need for local validation. And going towards spatial accuracy, globally speaking, regarding map accuracy, we have an F1 score of 0.90 and detection accuracy of 0.92. So here we can say that accuracy is highly dependent on the forest mask quality, once said before, and local land use complexity. So here are some small examples from Atalaya, Peru, June to July 2022. Kaonik, Cambodia, January to February 2022. Cartagena, Chaira, Colombia, October to November 2021. Akamke, Nigeria, March to May 2022. San Pedro in Cote d'Ivoire, January to April 2021. And Leguala, Honduras, from April to June 2024. Now going to the temporal accuracy, this research ended up with having a average detection delay of 14 days, and having most of the detections occurring, and 69% of the detections were confirmed within the same quarter of occurrence. So as a overall, we can say that this method is highly suitable for quarterly monitoring, but precision will vary according to canopy structure and signal noise. And yes, we have some limitations as well, such as narrow strip clearing from 10, 20, 30 meters. For example, in Brazil, produced weak SARS signals affecting timely detection. As well, forest mask errors, once again, accuracy highly depends on the quality of the forest masks. So local discrepancies can lead to false detections or omissions. Here, this is detected as forest, but in reality, it's a coffee plantation. And also seasonality confuses detection. For example, in dry forests, vegetation loss during drought can mimic deforestation, and during rainy seasons, regrowth can obscure the real changes that are occurring. So with this, I conclude my presentation. I'm really pleased that you were listening to me, and if you have any questions, you can ask me right now. And if you have any, if you want to dive a bit more, there's the QR code of my thesis if you are interested. Thanks a lot.
Thanks a lot, Jorge. So we have time for 2 or maybe more questions.
Thank you for the presentation. Was the entirety of your data analysis done within Google Earth Engine, or did you use other tools like Python notebooks or any GIS platform software? And are any of the scripts open source and available for review?
Okay, so in Earth Engine only was the preprocessing of the information, basically, just the preprocessing and downloading it. Then all of the script was carried out in Python, but I mean, it can be shared as well, because I know that it can be also enhanced.
Yeah, thanks for a great presentation. I was wondering, did you look into any like partial cuts or like where it's maybe not a clear cut? And because I think your method is very promising, but how well would it do with, yeah, not 100% a clear cut?
Yes, that's basically one of the limitations as well. For example, as mentioned, we have like, well, that will basically correspond on narrow strip clearings, that it's because of resolution gaps, it's not like we can't detect it almost immediately. So we will need like a bigger gap. So the clear cut needs to be a quite, let's say, big compared to the resolution. But thanks a lot for the comment.
Thank you very much for the excellent presentation. I am wondering if you considered using the coherence between 2 images as an indicator or index. It might be worth looking into, because I'm coming more from the interferometry side, so I'm not really well versed in amplitudes, but coherence is very sensitive to change, so it might be worth looking into in the future. Thank you.
Yes, that's true. It might be useful to adhere to it. In this research, we were only considering the backscatter distribution, but yes, that's a good point, that it can enhance this research. Thanks.
All right, thanks so much, Jorge, for this presentation. I think we can move now to the next one.
Thank you. Okay, so thank you. Now it's my pleasure to invite here Abdullahim Abdi to present, to move back north here to the hemi-boreal forests, or maybe also boreal forests of Sweden, and tree species classification. So the floor is yours.
Yeah, thank you very much. So let's see here. Yeah, so today I'll be presenting work that I did with my colleague Fan Wang at the Research Institute of Sweden. So what we try to do with this work is to develop a new tree species classification map for Sweden. And as you all know, Sweden, or most of you know, Sweden is a majority forest country with 70% of the land surface covered by forests. And by some estimates, it has the largest area of productive forest in the EU with about 28 million hectares. The distribution of the forest cover is primarily due to 3 species. Spruce, let's see here. Yeah, there we go. We have pine, Scots pine, Norway spruce, and birch. The remaining 8% are your regular numoral broadleaves, beech, oak, and so on. And this distribution of tree species is not uniform across the length of the country. So, for example, in the northern part, only 4% of the species are other than spruce, pine, or birch. Whereas in the south, where we are focusing, up to 14% are other species that are not the dominant ones. So our study area is focused on the southern part of the country because of this diversity in Götaland. And we used data from the Swedish National Forest Inventory as our primary source. And this is thousands of plots distributed across the country, circular plots, and they're spaced roughly between 300 and 400 meters in the south. And 60% of these plots are permanent, and they have a radius of 10 meters, and they're visited every 5 years. The remaining 40% are temporary. They're only visited once, and they have a radius of 7 meters. So we took all the data we could from both the permanent and the temporary plots. We went through a data cleaning process where we took away the plots that had signs of disturbances, like clear cuts, for example, and plots where the trees were relatively young, like recent plantations. We also took out plots where the forest didn't meet the definition of a forest according to Swedish law, which means that the trees had to reach a height of 5 meters. So after all that cleaning, we were left with about 7,000 plots, which we call high-quality plots that we could use for the modeling. And we did some preliminary testing of these 7,000 plots to see if we can get a decent accuracy for mapping different tree species. But unfortunately, because the spectral signatures of these tree species are all very close to each other, and same with the radar backscatter, we decided to increase the volume of our sample points because we didn't have the 7,000 plots were not enough. So what we did, we took a random sample of about 20% of those, and we went through each of these plots. And if you look at the 2 images on the right, the innermost circle is the original plot. So for each of these plots, we went in and we looked at the morphology of the canopy within the plot and the morphology of the canopy in the surrounding areas. We looked at the phenology as well to ascertain whether it is the same tree species within the plot and outside the plot. So in this particular case, the NFI says that this plot is 100% beech. So when we look at the canopy cover, if you look at the top right image, you can see that it is the same morphology inside and outside the plot, and the phenology also is similar in the bottom. So then we said, okay, this is a beech forest, which means that we can expand our footprint beyond the original plot to get more pixels in for the classification. We also visited several forests which were within a 2-hour drive from Lund with my field assistants there, you can see, to get more points in order to do the classification. And we also relied on Google Street View for the plots that were near the roads, near the public roads, and if there was Google Street View available. So in this particular case, this was a beech forest that was, the plot was here on the left side. And we were like, okay, this is a beech forest, and it's a continuous beech forest, and we can also geolocate it from the Google Earth imagery. So we did a bunch of things like this to increase our sample count, and we were able to quadruple our number of samples for the modeling. Then we used Sentinel SAR, about 1,300 acquisitions. Sentinel-2, about 2,700 acquisition between 2021 and 2023. And these images have gone through the standard pre-processing to get them to analysis-ready data. Then we created seasonal composites from this imagery for the 4 seasons. And we also included geomorphometry like elevation, slope, aspect, topographic wetness index, and also canopy height. And we put all this in a extreme gradient boosting model in order to get the classification. And after several iterations, we're able to get a fairly decent accuracy for tree species. So this is what it looks like. We have an overall accuracy of 85%. The F1 score was 0.82. Precision was 0.84, and recall was 0.8, which we were very happy about because our initial target was to get over the 0.8 threshold. And as some of you are aware, it's extremely hard to map or to classify tree species because of this spectral similarity. And the species area coverage is what you can see in this slide there. And this is, just to give you an example, this is an area that's about an hour away from Lund in the southernmost province of Skåne. And this is what the forest looks like. This is a very diverse forest, and it's managed actively by a foundation where they are experimenting with continuous cover and trying to increase the species diversity in the forest. And this is what the map looks like. I'm just going to go back and forth so you can see the differences. And we also created a uncertainty map from the extreme gradient boosting model. So what extreme gradient boosting basically does is gives you a probability vector for each classification. So we took that vector and we simply applied a Shannon's entropy on it. So high entropy, basically the red colors in the map, basically means that the algorithm is not sure which class this particular pixel falls under. And low entropy means that the algorithm is fairly certain which class it is. So so if you look, for example, here at these solid blue areas, so these are contiguous beech forests, and areas where the algorithm is uncertain are along the edges where one species meets another, right? And in areas where there's a lot of diversity, like mixed forests, for example. So, and then we also did an additional sanity check where we compared our map with the National Land Cover Database of Sweden. So they created, they have about 20 or 25 different classes, but they didn't classify individual species, but they classified forest categories. So these are some of the categories here that they have in the National Land Cover Map. And we've compared their categorizations with our species classification. And we were really happy that the areas that we have mapped really fit within their definitions, which was very nice to see. So for example, they define pine forest as any forest that is at least 70% pine. So we kind of have that. And the same thing goes for the other classes as well. So that was really, really cool to see, and for us to see that we're doing a good job. Yeah, and this is it. I think I have like 3 minutes left. The data, the paper is undergoing the second round of peer review, so it should be out in the next month or so. The data is already public, so you guys can go ahead and download it. And we also have a web interface where you can visualize the data and download chunks of it onto your own computer, both the classification and the uncertainty layer. And also in the data package, we also have continuous layers of the individual tree species where we've applied a uncertainty-weighted continuous moving window, like weighted fraction for each species. So that's there too. So you guys can use them. And yeah, that's it. This study was funded by the Swedish National Space Agency, and that's my contact detail. So yeah, thank you.
Thank you very much. Very interesting and clear and relevant presentation. We have a question up there. Let's start from there.
Thanks. Very nice and interesting talk. I have a question. When you presented the plot, let's say, or the number with the different categories of forest. Yeah. Yeah. No, this. Yes, this one. Yeah. So those numbers you show are the numbers that you get.
Yeah.
From your model.
Yeah.
By
sorry,
selecting
maybe I didn't clarify this very well. So the NMD is a raster map. So what we basically did was we converted that raster map into polygons. We superimposed those polygons onto our map to get the percentages of the different classes within each polygon class that they've created. So when they have, for example, when they have like a polygon that says mixed coniferous forest, we have that polygon onto our map, and then we count what the percentage of the different classes are in that.
Okay. Yeah. Thanks.
Thank you. Other questions? Okay.
Thank you for your presentation. I was just wondering if you can share some feedback about the computational demand of such a project.
The computational demand?
Yeah, pre-processing.
Yeah, so the data we downloaded, the raw data we downloaded from Earth Engine using the Python interface. But the processing, we did that on our desktops. And we have a GPU, and we just basically ran everything in-house. But the pre-processing of the raw data and the download of the raw data, that came from Earth Engine. We didn't download the images, the raw images locally. Yeah, we've had terabytes of storage in that CPU, so in that desktop. So.
Okay, thank you. I have a small question about. So have you so these are species compositions. So, but what about the data? So did you look at which data sources were most relevant? How relevant was SAR data, for example, Sentinel-1 in this classification?
That's a great question. I actually have that slide, but I didn't have enough time to talk about it. So we have the most important variable was the ratio, the multispectral ratio vegetation index, which is also called the simple index, the near infrared divided by red. And EVI was fairly important, band 11, band 7, the red edge band, and the VV, the vertical receive, vertical send receive was also important. Regarding the seasons, the spring and summer were dominant. I would have expected the autumn would be important as well, but not as much. So.
Okay, yes. Thank you. We have time for another question. Oh.
Thank you. Perhaps a bit in perspective, looking at this slide and looking at the relevance of B11 and B12, do you expect imaging spectroscopy and the growing availability of hyperspectral data, let's say, to increase these performances significantly?
Oh, hyperspectral, absolutely. I would think so. I think that if we have regular acquisitions of hyperspectral data, we would be able to like map individual species relatively easily, because if you saw in the previous slide that I had, that there is, where is it here? There is considerable variability between the reflectances of different species. And if we had hyperspectral data, if we had like a narrower band here, we would be able to pick those differences a lot easier.
Thank you.
Yeah.
Okay, thank you. Very nice question and a very excellent answer about the future hyperspectral data, which you shouldn't speak conditionally. It will be available. Lisa will provide it to us in 5 years. So thank you once more, and we move on.
All right, next we have Emma Turkulainen from FGI, who will talk about monitoring bark beetle using deep learning techniques. Welcome, Emma.
Okay, yeah, thank you. So my name is Emma Turkulainen. I'm from the Finnish Geospatial Research Institute. And this talk is about using domain generalization in bark beetle monitoring. Specifically, this means that we're trying to develop detection and classification systems that work well in varying environmental conditions without needing to collect new training data for each location. And So what is the problem we're trying to solve here? So deep learning models have become very effective in analyzing aerial forest imagery. So we can train models to detect trees and classify their health status or identify different tree species. And these methods work well when we have good training data from the target site, but there are still some issues that limit actual operational deployment. So when we train these models in one site and then we try to use them in some different location that may have a different kind of data distribution, then the models may not work so well. And this is called this domain shift problem. And in forest monitoring, this domain shift comes from many different factors. So for instance, seasonal variations. So the forest can look very different in the spring versus summer versus fall. And of course, there's also geographic differences. So the forest can have different species mixes and like stand densities and so on. And of course, there's these technical factors such as differing sensors and flight altitudes, atmospheric conditions, and also the weather can change between different imaging acquisitions. And this causes this consequence that when we want to deploy these monitoring systems to new sites, it may mean that we need to collect and label new data from that location. And this is, of course, costly and time-consuming, which limits the scalability of these models. So our goal was to see whether this kind of domain generalization framework can help kind of alleviate this issue and whether we can perform robust bark beetle detection in new locations without needing any data from the target domain during training. And in this study, we used data from 5 different forest sites in Finland. So we had Paloheina and Espoonlahti forest areas in the southern part of Finland, close to Helsinki. And these were these mixed urban forest areas. And then we had Evo, which is a research forest in southern Finland. It had mature boreal forest containing mostly spruce and pine trees. And then we had Ruokolahti in the southeastern part of Finland, which had managed and conserved forest areas with different kind of forest structures. And then lastly, we had the Koli National Park in the northeastern part of Finland, representing this northern boreal forest. And it had some substantial topographic variations, and in our data set also significant seasonal variations. And yeah, we used RGB and multispectral drone imagery, and the data was collected between the years 2018 and 2023 in spring, summer, and fall seasons. And in total, we annotated around 4,700 trees, divided them into 5 different classes. So we had healthy, infested, and dead spruce trees, as well as pines and deciduous trees. And when analyzing our models, we used this leave one site out cross-validation. So we trained using 4 of these forest sites and then testing on one that was not seen during training. And we also did this kind of TSNE domain analysis or feature analysis to reveal some seasonal and location-based clustering in the data that kind of also shows the domain shift. And here is a visualization of that. So here we can see this TSNE feature distribution of the Koli National Park across different seasons. So in each season we have the same trees, same location, but we can see that the data clusters very strongly based on the season that the data was acquired from, which is obviously not optimal since we'd want the data to be more separable based on the health and species classes we want to identify and not so much the season. And then this causes the issue, for instance, if we train the model using only the summer data, then it may not perform well when we try to use it for the spring and fall data sets, for example. So this is the issue we're kind of trying to solve. And in our approach, we use this two-stage pipeline, where we first use a modified YOLO v7 network for the individual tree crown detection, and then a simple CNN classifier to then classify the health status and species of the trees. And in this figure, we show the general architecture of this domain generalization framework. This is specifically for the classifier network. So at the top, we have the input image or images, and then this parallel feature extraction pathway. So on the left, we have the shared feature extractor, which aims to learn the features from the data that are task specific, that show the health and species of the data. And these features are supposed to be domain invariant, so these features should be shared across all the different sites and seasons and so on. And then we have this domain-specific feature extractor, which then aims to learn the domain-specific features which are caused by this environmental variation. And in the center, we have the key part of this framework, which is the gradient reversal layer. I'll come back to that a bit later. But after that, we have the classifiers. So we have the task classifier, which uses the shared features to predict the class label of the images. And then we have the domain classifier that tries to determine which domain the data comes from. But since we want these shared features to be domain invariant, we want the domain classifier to be kind of confused when trying to determine the domain based on these shared features. And that's why we have this gradient reversal layer. So during the back propagation step of training the network, when the parameters of the feature extractors are updated to kind of be able to learn features that are more useful to the classifiers, then this gradient reversal causes causes the effect that then the shared feature extractor learns to confuse the domain classifier instead of improving it. And this causes this kind of adversarial training scheme where these health features are separated from the site-specific variations. And here are some of the main results of this method. So we performed this leave one site out cross-validation and achieved 80 to 84% overall accuracy, depending on which site was left out. And this was an up to 27% improvement over the baseline approach, which didn't use this domain generalization capability. And in the figure, we have the class-wise F1 scores for the Colli National Park. I chose this because the baseline method was performing the worst on this site, and then this domain generalization method improved the results the most in Colli. And yeah, you can see that the results were substantially improved for all classes, and specifically for the infested and the non-spruce classes, which were the most difficult to classify correctly. And this performance is also comparable to site-specific trained models. So when using transfer learning and using some training data from the Colli site, we achieved similar results than when using this domain generalization method. But of course, we can still see that for instance, the infested class the F1 score is around 50%, which is still not quite good enough for real operational deployment, but it's still a nice improvement. And here we're just demonstrating the operational capabilities of this method. So we performed these individual tree-level damage maps of tree mortality in the Colli region. So here we didn't use any training data from Colli, but these maps were kind of visually verified to see that they were accurate, and this would not have been possible with just the baseline method. And this shows this kind of time series of the damage progression between 2023, 2024, and 2025. So you can then identify high-risk zones and see where the outbreaks are spreading. So yeah, as a conclusion, we could see that this domain generalization framework works. We got this 80 to 84% accuracy, which was a 27% improvement. And this makes it possible to use this model without needing any new training data from the new location where we want to use it on. So this is a very scalable pathway that allows for rapid deployment across large regions. Of course, there are still some limitations. For instance, the infested class accuracy still remains a challenge. And in this study, we only used data from 5 different forest sites. And of course, more diverse domain data would improve these methods more and allow for a more comprehensive analysis. But yeah, this study was based on, based on previous and expanding on previous research that I've listed here. But yeah, thank you for listening, and I'm ready to answer any questions.
Thank you, Emma. So we have time for a couple of questions.
Yeah, thanks for an interesting talk. I was wondering, the input of the deep learning model, is that just the RGB and the near-infrared, or do you do anything with spectral indices as well?
I don't do anything with spectral indices. It's just the spectral bands. Yeah.
More questions? I have a question. So in your leave one out, you accounted for the spatial variability, right? So you tested if your model performs well in different locations, but did you also test it like different seasons, how it is affected?
Yeah, we did also test on different seasons, and I don't have it listed here, but yeah, the results also improved a lot when compared to the baseline. So, for instance, in the Colli, we had the spring and summer and fall, and we could see first like the data was clustered a lot based on the season. And then when we performed this TSNE analysis, kind of on the model that was trained to generalize well, then we could see less clustering between the seasons.
But I guess the performance declines quite a lot by autumn, or not, as the spectral signal starts to homogenize a bit.
Sorry?
Does the performance of the model decline a bit during autumn, maybe, or not? Or is it the same as during summer?
Oh, yeah. Actually, we got the best results from autumn.
Okay.
Yeah, which is strange, I guess, but yeah.
All right, good. All right, thanks a lot, Emma, and I think we can move on.
Thank you again. And the last presentation of this session comes from Arjan Medens about forest disturbance and carbon. So, the floor is yours.
Thank you. Let's see if this works. Could I go forward? There, okay, I'm backward. All right. All right, thanks for having me, and I've been really impressed with the talk so far, so a little like, who am I going to follow up with this? So I'm Arjan Meddens. I'm originally from the Netherlands, but I have been in the US for the last 20 years, and I'm now an associate professor at Washington State University. But I'm also here for a year for my sabbatical, and I've been hosted by Luque. So I've been here the last maybe 6 months at the Viki campus of Luque. And this is sort of my sabbatical project that I'm here to present. So just a little bit on the introduction or motivation of the study. So we all know that the climate is continuing to change and we're getting warmer. And we also see that the European forest disturbances are actually increasing. And then here's a recent paper that actually shows that it's going to cost us, or it's projected to be going to cost us more. So if we look at like the historical, we're like at 100 billion and might even increase to 200 or even more in the future. So it's important to look at these disturbance impacts on forest productivity. And then so so the other thing is like it's important to estimate these total carbon fluxes to develop effective climate change mitigation strategies, and also to like sort of track the efficiency of how we could like reduce greenhouse gas emissions. And then finally, it's interesting to just learn more about it. How can we better understand the global carbon cycle? But has anybody have an idea what the sort of the total annual global vegetation productivity is? So the total productivity of vegetation on the globe is about 130 petagrams of carbon. So that's an estimate, but yeah, that's a whole lot of carbon. And honing in on that number and getting a better idea of what that exactly is important. But how would you estimate that, and where are the major uncertainties? That's the question. So you could, for instance, estimate that using flux towers or even forest inventories, but then you have only these like point estimates, and then you have to scale that across space. So another way to do this is dynamic vegetation modeling. So then we have these complex computer models that we run at a time step and sort of integrate the whole vegetation growth. But as we're all here, remote sensors, more interesting is to use a light use efficiency model. And that's been like done more and more. And that's where we can sort of estimate gross primary production using PAR, so that's the photosynthetically active radiation. And we multiply that by sort of the fraction of the vegetation that is actually absorbing that radiation. And then we sort of modify that by the efficiency that the vegetation can sort of capture that carbon. And that's depending on what kind of vegetation you have, or also what temperature or how much moisture there is. So basically, this is a general way of how these models work. There are some uncertainties, as with all these models are, but so some of the major uncertainties are, well, we're only measuring often just the top of the canopy, so we don't know what at the second or third layer down is happening. We also have a relatively short time span of these available satellite data. And then what I'm sort of focusing on is what are the effects of disturbances, and are we capturing those? Okay, so just 10 years ago, we actually did publish a study on this in north central Colorado, where we looked at the carbon impacts of a bark beetle outbreak. So this is over here. Sort of Denver is sort of over there. So there was a large mountain pine beetle outbreak, and we could actually show that like the most severe, here in red, the most severely affected areas really showed a steep decrease in productivity. And if we then sort of like related that, the decrease to how much of a grid cell was affected, we could see a pretty good relationship between, saying like more affected forests had a larger decrease in productivity. So this was basically my idea to do this for Northern Europe for different disturbance types. So that's sort of what I undertook starting in August here, and with the ideas like, can we quantify and compare these carbon dynamics across Northern Europe, looking at these forest disturbances. And so I've used these data, I'm going here from the bottom up. So I'm using the MODIS annual gross primary productivity data set, but I'm also including a more higher resolution Sentinel-based data set. And then there's a recently published data set based on Landsat that actually detects all the disturbances across Europe. And so by combining these, I would get at the productivity impacts, and then I can then estimate like how much these different disturbances are impacting. So that sounds simple enough, but it's never as simple as when you start looking at the data and start wrangling with it. So a little bit more background on the different data sets. So this is the MODIS land use efficiency model, MOD 17, and it's sort of one of the benchmark data sets that has been used to estimate global productivity and stuff. It's based on MODIS. It has a 430 meter spatial resolution, or around 500 meters. You can get it annually or even at an 8 daily time step, and it's available from 2001 to the present, basically. And then I've also used a higher resolution productivity data set, and this is actually not a land use efficiency data set, but it's more based on phenology. So it basically calculates the integral of all the growing season retrievals of Sentinel data. So basically, the integrated gray area over here is the total productivity over the growing season. And this data set is also available across Europe at a 10 meter spatial resolution, but only from 2017 onward. And then the forest disturbances, again, comes from this Landsat-based product that is just recently published. So this is a 30 meter resolution, and it, okay, thank you. It has, so basically different disturbance agents. So we have wind, bark beetle, fire, and harvest. And it's an annual data set starting from 1985 to more recent. Okay, so then how do we create these, like the impacts on the disturbance? So basically, we might have a pixel trajectory over here, that's maybe the baseline, but then we can look at like, oh, here there's a disturbance occurring in 2017 or so. Then we can sort of look at like that pixel that is being disturbed and nearby baseline data, and we can subtract that and get sort of the anomaly, sort of the difference in what we would expect from a normal and undisturbed pixel. And so then we can look at the decrease of productivity following that an outbreak or a harvest or something like that. Okay, so then we can use that to sort of look at the how much the disturbance fraction is and how much the productivity is decreasing. So here, for instance, for harvest, if we have like a pixel that is 100% affected, then we can sort of see what would be the expected decrease in GPP. Now for MODIS, and this was a bit disappointing, we could only see that we have like an R² for harvest is 0.2, so that was kind of disappointing. Fire was a little bit higher, but it's still it's not a whole lot of observations, and also not very well. And then for wind, also pretty poor R². So not only the R² was low, but also the impact is fairly low. If we would expect a higher decrease in GPP at 100% harvest of a pixel. So this was actually not so good results. So that's why I also wanted to include a higher resolution data set. So that's this HRVPP. And that actually shows a bit more comparable what we had earlier in the US too, R² of 0.5 at harvest, and fire maybe a little bit lower, but still an improvement. And same with the bark beetles. So the R² was better, but also the impact is a bit more realistic. We're going to like minus 45% carbon at 100% affected. So this seems a bit more realistic there. So that brings me to the conclusions. This is still ongoing work, so I'm still working on this, but basically the MODIS land use efficiency algorithm is not sensitive to these disturbances in Northern Europe, and that has big consequences. If we're not capturing the disturbances, then maybe our benchmark data set is not totally correct. So therefore, I'm posing that we need higher resolution data sets like the HRVPP data set to maybe integrate or supersede this MODIS algorithm. But note that this HRVPP data set is not a light use efficiency, or the units are not in carbon, so we still need to do a step there. So that's basically what I'm saying here. We need higher resolution vegetation productivity models. And my next step will be to expand this across Northern Europe and really come with some estimates of how much the productivity is impacted by these different disturbances. Okay. Thank you.
Yes. Thank you. Very nice, interesting presentation and a very relevant topic, for sure. But do you have questions now? So I have a question about, so why is it different from Northern or the US and America or here? Is it different species, or is it some kind of management? The scale is different, it's not so big as in the US?
This is a really good question. I've been wondering this too. Like the bark beetle outbreak that we were studying, it turned the whole forest totally red, and it was very progressive and very continuous. Here maybe our harvest patches, for instance, are smaller than the total pixel of the MODIS, and so there's a lot of like mixing going on, and maybe that's why I'm not getting as good of results there. So, but yeah, that's one of the things we've been trying to figure out.
Yeah, but could it be that if you looked at Central Europe and about 5-6 years ago when there was this huge bark beetle breakout, that there you would have forests or landscape that were devastated by the bark beetle, but that's actually, I think there in the Northern Europe the outbreaks are not so massive. Right. What could be?
Yeah, no, I think that's also a good point. And next step, I want to go to Germany, Northern Germany, or like maybe Central Germany, actually, where we need to go to have a look at that. So, yeah, that's a good point, and that's what I want to do coming up. So, yeah. Okay.
And you trust the MODIS product? You think they are?
I did trust it, and now I'm like, and actually over lunch we're talking about maybe the NDVI. It's based on NDVI out of the box, but the EVI or the EVI2 is actually maybe a better one to use over here. So, yeah, another thing to look at.
Until we have the hyperspectral productivity product from Europe. Okay, so thank you. Let's thank again all the presenters. And also a big thank to all of you who listened. And now let's break for a coffee, and there will be a vegetation session in, at what time? About, to remember that. Oh, just, does anybody remember at what time do we reconvene? At 35 past, okay. So 30 minutes plus for coffee, and then see you again.
pleasure to co-chair this session. I'm Olli Ihalainen from VTT, here with Teija Thum from FMI, Finnish Meteorological Institute. And the first speaker is Hassan.
Okay, good afternoon, everyone. I'm Hossein Aghaboubayi from University of Twente. Here I'll presenting the outcome of our work, which is an ESA-funded initiative with a consortium of four partners from University of Twente, from Netherlands, and then University of Partner from Italy. We have Aalto University and ET Forest Service Group from Finland. So what we do here is we want to assess what is the possible pathway to get the forest height from the open access global availability of the Sentinel-1 data set. Given the worldwide coverage of the Sentinel dataset being open available dataset, this would be interesting opportunity to analyze, in a sense, to what extent we can extract forest height from the Sentinel-1 dataset. So this is the main contents of our project. And in the SAR community, the most standard and straightforward approach for estimating forest height is the two-layer scattering model. What is it? We assume that forest is a two-layer model from the ground layer and the vegetation above the ground. With this model, we can have this two-layer equation, which represent the interferometric coherency as a function of several parameters, like H is the indication of the forest height, with mu indication of the ground, backscattering from ground to the volume ratio, and of course also the extinction or attenuation parameter represented with sigma here. So you see it, there are the interferometric coherency is linked to the several parameters. And this is indeed an ill-posed problem. We have one measurement with some unknown parameters. So what happened in the literature or state of the art, we use the polarimetric dataset, full polarimetric dataset because we have plenty of polarimetric interferometric observation, then we can retrieve this parameter and solve the unknown parameters, which one of them is, of course, forest height. But moving to the Sentinel-1 dataset, there are several issues arise here. One of the main important things is that Sentinel-1 is repeat pass. It means that we have every 6 or 12 days one acquisition. Then within this time interval, from radar perspective, the backscattering can change. This means that we have another contribution, which is temporal decorrelation, which limited us to implement this physical model to retrieve forest height. This temporal decorrelation is well known in one of the main challenges of Sentinel data sets. But one thing is that they discussed also more in the state of art is this baseline of the Sentinel-1 data set. So if you look at the Sentinel baseline compared to the Tandem X, the baseline is very small, so barely exceeding 150 meters. This results in to have a small KZ in that equation and make the volume coherency approach to 1. And what does it mean? It means that make the volume coherency less sensitive to the height within this model. And then we have also less observation. We do not have a full polarimetric data set, but dual polarization data set. So with this limitation, what we can do? Of course, we can follow some strategies to somehow cope with these issues or challenge. One of them is that if we have a repeat path acquisition, we can, of course, include the temporal decorrelation models. If we have a small baseline, we could assume that, or we could use those models under zero baseline or near zero baseline assumptions. And we can also put some, let's say, external assumption on the model to still be able to solve this unknown parameters with dual polarimetric data set. So having a near zero baseline, we can assume that, or we can model the interferometric coherency measured by Sentinel-1, which is on the top part of this one, the gamma. gamma T1 and T2 is the interferometric coherency between two acquisition as a function of those parameters you see here. Still, there are many parameters you see here. For example, we have delta V, delta G, which is the motion of the scatterer at ground level and the vegetation level on top of the canopy. And we have the attenuation, signal attenuation. We have ground to volume ratio. But it's not difficult to assume that most of the decorrelation or movement is not coming from the ground, but coming from the canopies or vegetation. So with this consideration, we can assume delta G is 0, and the ground to volume ratio also remain constant. Then we can simplify this temporal decorrelation model into this bottom line here. And yet we have, those are 4 unknown parameters: delta V, which is the motion of the scatterer, ground to volume ratio, attenuation, and the most important part is the forest height, which is H. So the solution is how we can solve this equation. If we don't forget that we have a dual polarization data set, so we can perform optimization, which is also known concept in the radar polarimetry. Then to find two polarization, which one of them is less sensitive to the ground contribution, or we can assume there is no ground contribution on that. So we refer to it as gamma maximum, and then we have also gamma minimum, which is the maximum contribution of the ground. So with that one, then we have those two equations, gamma mean and gamma max. In gamma max, the mu or ground contribution is almost negligible. And from these two equations, we can directly compute the ground to volume ratio with this equation. And with the gamma volume, we have that optimization. In the gamma volume, there are 3 unknown parameters. One is forest height, canopy motions, and then also the signal attenuation. So we have the Sentinel data set which cover the global forest, and then we have also LiDAR data set which derive from JEDI or ISAT. So they are also covering. So if we collect those data sets, I mean, at the global scale, we can get the forest height from the LiDAR data set, and then with this optimization, which is the difference simply between the model coherency and measured coherency, we can get those 2 parameters. So if we do this at the global scale, we can look at the pattern of this, those 2 parameters and get insight to maybe to develop some things to later to use to estimate the forest height. So to do this, we developed just automation process to download Sentinel dataset at the global scales, global forest regions, and also match them with the LiDAR datasets, either from JEDI or ISAT. So this is the simple and straightforward procedure, pre-processing step done. So we have the 2 Sentinel image, master and slave. We co-register them, match with the LiDAR dataset, and at the end you have a Sentinel image with some pixel have the LiDAR measurement, because those spaceborne LiDAR are quite sparse. We don't have a continuous image for all the image. So what we do it after this one, we collect the data set over global forest system, and we look at the statistic of this data set. So this is, for example, the distribution of the data set. We do have it here. I just speed up this because I have just 3 minutes left. And you see that in our data set, we have plenty of the forest measurements, like millions of the pixels, with the forest height starting from 0 to 50 somethings over the different ground topography, flat or mountainous region. And then we follow those strategy to estimate the parameters of this 2-layer model. One of them is the ground motions, canopy motions. If you see, there is quite a visible pattern between the height and canopy motions, and also between the coherency. So this is very interesting. It gives us an idea to maybe model this with a simple exponential function, describe this relationship with exponential function, and later use it to get the forest height model. So this is one interesting observation. And we also look at the other parameters like the ground volume ratio and also extinction, while in ground volume ratio, you could see also some pattern, but not at all in the extinction or attenuation of the signal. So what we did it to consider simply model the canopy motion using an exponential function like this one with coherency, interferometric coherency. Then we fixed indeed one of these unknown parameter, and then 2 parameters left, which is forest height and kappa. Then we can perform this minimization this time to get the forest height. To test the model, we just consider study area in Kotka nearby here. We download 4 pairs of the Sentinel image here. This is just the image, shows the interferometric coherency, the average interferometric coherency. And here are the results. So the top part is that result forest height derived from the completely physical model, standard, it's the 2-layer model. The bottom line is the reference LiDAR height. So yeah, that's not accurate enough. It's clear, but we shouldn't forget that we are working only with Sentinel dataset with a lot of limitation. And this is something we can retrieve from the Sentinel. And of course, you could notice some underestimation on the forest side. But still, the interesting part is to see is the pattern. For example, you see some region with the lower forest side, tall forest side. They are, the pattern seems escaped, is understood by the model. So what we can do next, we can use this one or with machine learning model to improve this result. So this is what happened in the next stage. We just use this model of the deep learning model. It's a simple and a light version of the fully connected neural network. So we train it over global data set, and then we have trained model. Now we test it on the Kotka study area, and here is the result, which improved a lot and gives us the opportunity to compensate the error derived from the physical model. Actually, this model is trained to correct the residual height between the LiDAR-derived height and RMOG or 2-layer model. So we correct with this model the residual height and then add it to the estimation of the 2-layer model, and we get this one. So if I want to summarize, yes, definitely when it comes to the application of forest height estimation with Sentinel, we face a lot of issues. We need to consider this limitation. Of course, we need to accept the possible difference between C-band and other L-band data sets, which limit us indeed to get higher accurate data set. But with machine learning, we still have this opportunity to improve the result and get some offer also, let's say, pathway to retrieve forest height with this open access data set. Yeah, thank you very much.
Thank you, Hossein. Would there be any questions for Hossein about this work? I don't see any, just a quick one because of the time. How do you think that the assumptions you were making in the first stage with your sort of radiative transfer model before the machine learning, do you think that they possibly influenced the results?
Yeah, definitely influenced. As you see in the result, you see there are quite a difference between the estimated forest height from the physical model and this LiDAR dataset. Those all contributing to the result. So if we have more polarization, more observations, we could lighten this assumption, and maybe we would be possible to get a higher accurate dataset. But with Sentinel-1 datasets, I mean, we have to do it. Okay. We have to sacrifice some things.
Okay,
yeah.
Thanks a lot.
Sure.
One more thanks for Hossein.
Thank you very much.
Yeah. And the next speaker will be Ilkka. So talking about Korpela from the University of Helsinki, talking about angular
On a related topic on how tree locations affect spectral reflectance, Matti, the floor is yours.
Okay, good afternoon. It's a pleasure to be here and present our results on the spatial distribution of tree crown locations in a boreal forest and its effect on spectral reflectance and how it can be modeled. So what I will talk to you about is why the spatial distribution of trees matters. This is stand level clumping as we talk about it, so there are different levels of clumping in the canopies, how we can quantify it, and how it's optimally measured from real actual measurement data. And then some measurement results with a very nice data set that is, has become available recently. It's part of an ERC project by Aalto. And it's a team presentation, so there are co-authors from Luke who have done the theoretical work, for example, and the data processing here also done by different people. So why is it relevant? So on the average, natural forests are relevant, and that's a big discussion topic also in Finland. And the question is that how do you separate, distinguish natural and artificial forest, or an old forest or an old growth forest from the ordinary forest that we have? And on the average, they have a more clustered spatial pattern of trees. Of course, it's not a unique feature. You can have clustered new forests which are not old grown, and you can have quite regular old growth forests or more regular. So, but it's the most significant statistical feature that separates at the general level these natural and so-called non-natural forests. So it's relevant for general purpose. And also it affects radiation interception and thus reflectance. And in remote sensing, one of the key tasks is to get forest parameters from reflectance. And there's kind of it's a hidden parameter. It's there whether you like it or not. So we need to, if we want to model forest reflectance in order to come up with a better way to invert our remote sensing data, like from Sentinel-2, you need to know which value to use. We have some understanding, but we know that it depends a lot of things. But theoretically, what I present here, this is basically the single mathematical equation I will present. Do I have a pointer here? Is it? Oh, that one. No, probably I don't. So the equation here tells that the transmittance of a canopy to optical radiation, so if you look up or down, is exponential function of basically some kind of leaf area. This is a Bouguer-Lambert law, very common in all kinds of remote sensing. And if you have taken into account the concept as a tree crown, so it depends on two things, the exponent, its number of tree crowns and their projected area or silhouette area. So if you have a larger silhouette area or a larger crown, you have less transmittance. And this drives basically reflectance. So reflectance and transmittance are connected, not in a linear way, but basically you need to model canopy transmittance. If everything is completely random, then we have what is known as a Poisson canopy, so a canopy that's created by a Poisson point process. It is just exactly the product of the two in the exponent. So transmittance, logarithm of transmittance is number of tree crowns times their surface silhouette area, which is silhouette area is their projection area times their transmittance. But if it's not regular or not completely random, then you have a factor of C in the equation. And this is just a very simple question. How do we get that C into the bottom of the screen, and how do we model it, and how do we understand it? Because that C probably most likely describes also how natural a canopy is. So it's a kind of a key variable, which is quite often overlooked. And how to quantify it? Of course, now we have one parameter. There are different statistical measures, so my co-authors are better experts on that, and there are many papers on that, mostly decades old. But we also know that if you have one value C, which is this clumping factor, it can be produced by many slightly different or very dramatically different physical processes or tree distributions. So we need some kind of a further model to restrict what the forest would look like. So how to generate this forest or how to represent this forest. With one clumping parameter may not be enough, but at least we should get at least one parameter. That would be a step forward, because until now what commonly people use is 0. And fortunately there is a single parameter in a single radiative transfer model, and it comes from the assumption that if the number of tree shadows is binomial, so there's some simple mathematics there, you come up with an equation that is in the ellipse, that you get an exactly identical equation, and we have a mathematical equation that is equation 8 for the C. It's not a simple equation, but it connects our clumping to a statistical measure we can, or transmittance to a statistical measure we can measure in the field. And that thing is the Fisher's grouping index, the relative variance of the number of trees in the area of a crown shadow. So this is basically currently the best approximation to the holy grail that we have in terms of tree statistics. So we need this Fisher's grouping index. So and this is a very old index. The previous paper that was published, okay, it's published in 1909, but the work was done in the 70s and 80s already by Diet Nilsson from Tartu Observatory. And it's a very simple index, so you take a specific area, projected area of a crown, throw it around several times in a forest and count the number of trees that happen to be within that area. If the variance of these many samples is the same as the mean, you have a Poisson canopy. Your Fisher's grouping index is 1. If it's smaller than 1, it's a regular canopy. If it's larger than 1, it's called a clustered canopy. And it's not dependent on tree density, so it's not scale dependent. You can have several Fisher's indexes for a very different density canopies, but it's dependent on the selected area, and it needs to be the area of a crown, so it's a dynamic quantity. It's not that you have it the same for all forests. But in real life, okay, I'll touch it slightly. We need to define what is a tree. Trees are like that, or like 20 meters tall. You see a small tree there in the front, a larger spruce there, and then lots of birches. Which ones do you count in when you count the trees? That is a different question. I'll touch that in a minute. But to do the experiments, we had a good data set. This was measured in 2009 over Hytiala, and it included on a Czech Globe-operated aircraft, airborne laser scanner with 48 hits per square meter, and also full hyperspectral reflectance, visible near infrared and shortwave infrared. There were also ground-based measurements. We didn't use them, but there was terrestrial laser scanning involved and spectral measurements. So we actually have a very nice spectral data set. It's not produced by us, but it's freely available to everybody. It's open data. And on top of that, we had Joel Kostensalo from Luke do us the individual tree detection. He has worked on that a lot, and now he's academic research fellow on the same topic. So we have state-of-the-art tree locations from the very high-density laser scanning data. We know where the individual trees are. We know how to correct the distributions for undetected trees or over-detected trees. We have some information on how to turn tree location into canopy cover. For that, we need actually not only the location of each tree, but how large each tree is. This is not so easy to see from LiDAR because tree crowns do overlap. So we used allometric measurements, which are unfortunately not very accurate. But we could compute the clumping index on a 16-meter standard grid used in Finland for Finnish forestry, and also get all the other required parameters out to further do this reflectance modeling. The first test is, do these transmittances match the transmittances measured by the scanner? So we have two measurements. With simple canopy transmittance of laser scans, we have one value of canopy transmittance in 16 by 16 meters square. And then we can do the complicated way of computing canopy transmittance is we compute Fisher's grouping index for each cell, then we take and then use the allometric relationship between tree height and canopy cover, or tree height and crown cover, and use the Fisher's index and calculate transmittance. And what we see is that it's not very good, but there is some signal in it. And based on that, we could choose different kind of trees, include all trees, but we finally decided that we include all detected trees and only detected trees, no fill-in. As an example, what it looks like, so this is the airborne strip in Hyytiala. Zoom in a bit on an area. Here there's a birch forest. There I'll show detailed data here. This is quite detailed, most detailed image you see here. This is the image. You see this is birch forest at the bottom, and spruce is growing in the between. We put or higher up, further north, so we put the grid on it, then individual tree locations, and we compute the Fisher's grouping index. You'll see the values later. And you notice that the red values, these are regular, and bluish, greenish is more clumped. And at the same time, we also did tree density, so the right-hand image is on tree density, and the numbers there show the top number is tree density, and the yellow number is grouping index. So there are two cells circled, which have about the same tree density, but very, very contrasting Fisher's index. And this is actually quite interesting, because you can look at it and try to see what makes a Fisher index different. Visually, at once they seem quite similar, the locations, but actually if you look at it, in the topmost cell you have trees that are close to each other, so it's clumped. And although there are big gaps in the bottom circled cell, like in the top left there, there's a gap there, but there are no trees close to each other, so this is a regular cell, let's say, regular forest. And these forests are different. So further zoom in on another location where you see that there's a kind of feature up there. I think it's pine forest, and there's a cutout forest stand, which when you look at Fisher's index, you can see that there is patterns here. This is stem density. You see that it's kind of bluish somewhere. You see the scales here. But when you look at Fisher's grouping index, you see that the cutout actually stands out clearly. So there is completely different information content in these two, stem density and Fisher's grouping index. So it's an interesting parameter, at least. Now, finally, in the last 2 minutes, I get to forest reflectance modeling. So on top of this transmittance modeling, there is also a reflectance model built on top of that using the same parameters, including canopy transmittance, computed using Fisher's grouping index. It's an old model implemented in Fortran 77, and it includes the Fisher's grouping index to simulate canopy transmittance to produce the reflectance. It's been validated in Finnish forests, so this is earlier published paper by Eelis that shows that what kind of accuracy we expect to get with the data that's available in spectral libraries, and this is Metsäkeskus or Finnish Forest Center data, so it should work more or less. Of course, there's a scatter. And then we try to simulate the forests in Hyytiala, so this is the hyperspectral red, green, blue mosaic. Put on top of that, simulated, well, visually you see some patterns, so we get at least some structure out, we get a realistic signal, and this is work in progress. You see the vertical lines, these are laser scanning tile-related problems, technical things we can overcome. And the problem is, so do we see the Fisher's grouping index there? Do we see an advantage of the best estimate versus the baseline scenario? Visually, it's very difficult to see. There are two bands, but this is the outcome, basically. The best line, the difference between the baseline, 0.20 Fisher's grouping index, which is the tree density distribution parameter of 2.2, so that was I think the optimum Eelis used, versus the dynamic FGI related thing. And it's kind of less, invisible bands is less than 1 percentage point, okay, because the reflectance is very low. but it is there. And our next step would be to try to tease it out from the reflectance signal and actually make use of it, see if we can make use of it using maybe, if not Sentinel, then future hyperspectral data, because then we can freely choose the spectral region which is most affected by it. Now, currently it's dominated by uncertainties in understory reflectance, our uncertainties in leaf spectrum, uncertainties in everything, in addition to the uncertainty in this tree distribution. But if we narrow down the other uncertainties, especially the non-photosynthetic materials in the red and near infrared, I think we can get closer to that forest reflectance parameters. And then maybe someday, merging with other data, we can tell from purely remotely sensed data that this is a natural forest and that is not a natural forest. Maybe. But, well, that time may come or may not, but we'll see at least. It's an interesting topic, I think, and it's quite an overlooked parameter, completely new source of information, potentially retrievable from remote sensing signal. So, thank you.
Thank you, Matti, for the very interesting talk. We have time for one quick audience question. Is there any?
Okay.
Do you think that we can first agree upon what's natural and what's not natural?
That's not my problem. Let Luke handle it.
Okay, if there's no further questions, then let's give another round of applause to Matti. And our next speaker is Tea Thum from FMI, Finnish Meteorological Institute, on sun-induced fluorescence from space. Floor is yours.
Thank you, Olli. And thank you, everyone, for sticking around so long. Yeah, I'm not a remote sensing expert. My background is in vegetation modeling. So I'm interested in sort of using remote sensing data to sort of improve my models and benchmark them. Because this might be a bit new topic, I will give a short introduction what I will be discussing about. I will introduce what chlorophyll fluorescence is and talk a little bit about carbon cycle and then go on to the modeling, the measurements I'm using, what kind of issues I will have with the different scales from the remote sensing and the actual measurements, and can I really get that kind of information that I would need from the remote sensing data I was trying to use here. So the chlorophyll fluorescence is emission from plant leaves, which is part of the absorbed radiation. Here is a conceptual figure on the right-hand side, or left-hand side, sorry, depends which way I stand. So it's a near infrared signal, and it's related, not directly, but linked to photosynthesis. And we can observe this from leaf level, canopy level, or from space. So what I'm using here is data from Tropomi, which has been lost in spring 2018. And it provides close to daily data. I mean, this sort of spatial resolution is really, really good for kind of purposes that I'm interested in. The footprint is 7 km to times 3.5 km at nadir. So it doesn't match exactly what I'm after, but does it really matter? That's one of the questions. And here is the cross-primary production, basically photosynthesis. These are from flux tower observations from Sodankylä. Here is a figure from the Sodankylä flux tower, currently also part of the ICOS network. So we see on the sort of, in the middle, we see diurnal cycle during summer of the GPP. So this is photosynthesis. It starts to increase when the radiation starts. Early in the morning increases for the summer, for the midday. And because this is Sodankylä and close to midsummer, you can see that the increase starts very, very, very early. And the black line is always the observations, and the colored lines are then the model, because I'm using a Quincy model here, which is made for catching the biogeochemical cycles, and it can be used at different scales. So I'm now using it for site level stuff, but the aim is at the global scale, and that's why there is a lot of interest for the remote sensing data. And on the lower panels here, I have the monthly diurnal cycles, as long as then the full yearly cycle. So photosynthesis starts to increase in spring here around April, and then it decreases around October. In this study, I'm using 2 boreal forest sites with conifer tree species, one from Canada and then the Sodankylä site. So both of these sites have the eddy covariance flux towers, which enables getting the continuous GPP estimates, and they both also have in situ observations of the SIF. So SIF is the chlorophyll fluorescence, but it's called solar induced, which is then the chlorophyll fluorescence in natural illumination. So this is what it looks like. So this is the Canadian side, 2 years. On the upmost panel, I have GPP going up in spring, going down for the winter, and then again for the second year. The tower SIF, so this is now the in situ data. This is following the pattern from the GPP observations quite well. And this, the lowest panel, is now the tropomi product, so troposif. And we see a lot of the seasonal pattern here. So I was myself surprised when I saw this, that it's capturing so well many of the seasonal features. Obviously, it's not perfect. And one of the reasons is that this was 0.5 degree times 0.5 degree resolution. But yeah, with the remote sensing data, we need to get rid of the random error also. But one might question this, like, can't you do like any better? I mean, it's quite coarse resolution. But if I would take only the points that are where the site is located in the pixel, it looks like a random noise. So that's the same plot for the 2 years, and this is for reference with the coarser resolution. And this is only for the fraction of points. So that doesn't look like it's going to do any help. How about the land cover? I mean, it's evergreen needle-leaf forest. Like, just use the land cover information to filter out stuff. One thing, MODIs and high latitudes don't like each others. It hasn't been optimized for this. So we can look at here, for the Canadian side, with the 0.5 resolution data, 65% of the region is classified as woody savanna. Some of it is evergreen forest, which is good. For the Sodankylä site, I don't have any evergreen needle-leaf forest. Actually, the site is located in this product is located is classified as savanna. So this is not really a way forward. This is a known artifact of the MODIS data, and we must be careful with it. And I was using this because it's in the troposif product, and this information is not used to calculate the output of the product, so it's just for reference for this kind of analysis. When I did the plot for the 0.25 grid, so some less points, I thought first like, oh, it looks a bit better. But then when I calculated the metrics against my model, it seems like, nah, I'm still getting slightly better performance when I give the rougher resolution. Is my model the right reference? Maybe not. I was also checking the observed GPP versus troposif relationship, and that was giving similar results. Why do I care? Why do I want to use this? Why am I doing this? So this is the same plot as shown for Canadian side for the Sodankylä site. For year 2021, I have only 1 year of data there. And here, I'm not having data. I'm not having in situ data of the tower SIF, but I would really like to sort of like to know how to get my model working, because if you plot my current modeling here, it kind of looks that it's starting really early. I mean, the SIF is starting far before the emergence of GPP. And this is because I would actually need to really parameterize non-photochemical quenching, which is decoupling the SIF from absorbed radiation. Would be great if I could use this. Can I? I like to be optimistic, but relying on that would be maybe too optimistic. If I have now shaded here the region that it seems that this is really the time when the sort of GPP is starting off. Something happens in the tropospheric signal, but then it actually starts to go down, and then where the blue line is, it starts to go up again from the zero, but already at that point when we look at the upmost figure, the GPP is already like halfway of the summer maximum. So it's a high latitude place, so we don't have that much data early in the year. So that might be one bottleneck here. But yeah, based on this, I would not use it. Because I'm optimistic, I will still try with some more data, with a longer time series. But yeah, worth the try, I think, but no, not betting on that. So to conclude, having these 0.5 degrees, even though it might sound like ridiculous, especially here after hearing talks about 30 meters, 10-meter resolutions, but for me it looked at it's kind of robust, for my needs. And then for this Sodankylä site, it's really not the way to improve my parameterization, which is in a way of pity, but we have in situ data there, so I hope that I can find some more links with longer time sets, data sets. And yep, I was thinking of having here one slide saying thank you and listing my co-authors, but I do not have that, so that's why I want to thank everyone for listening. Thank you.
Thank you, Thea, for the very interesting talk. Are there any questions from the audience? Matti.
Thank you. Interesting to see that, not the problems, but the presentation. But did I understand it correctly? So there's a problem likely that there are plants which change their photosynthetic apparatus in the early spring when the sun goes out, but you just don't see there when they change their NPQ level sometime in the spring and start to photosynthesize. So you have a fluorescence signal, but no photosynthesis in the early spring months. Was it
Sorry,
the problem?
that was not clearly said from my side. Yeah. So what happens is that in the model, without having the NPQ, the SIF signal, simulated SIF follows very much along the absorbed pair. So I need to add in the NPQ, a sustained NPQ there.
Where would you get that? Are you thinking of satellite products, or is it measured in the flux tower somehow?
You can get it from the leaf level observations by MoniPAM, from the active observations. And so what I've done for other sites, because for the Canadian site it was following all right, there I was able to sort of use a parameterization that had been done for Naivo Ridge site, which then made a really nice fit, but it didn't work for Sodankylä. So I would really like to have more data that I could parameterize that for the Sodankylä site and also get like a view, I have a global model, how to do that at global scale.
So you need NPQ at global scale?
Well, I mean, yes. One needs to do some assumptions, but to be able to use this model at global scale, also for these ecosystems.
Okay, any other questions? If not, let's give a round of applause to Thea. Thank you. And then today's final presentation by Asfah Mahmoud on fractional vegetation cover and land surface temperature. The floor was yours.
I'm a doctoral researcher at the University of Helsinki. I'm part of Earth Change Observation Laboratory. Today I will be presenting evaluating association of fractional vegetation cover and land surface temperature across spatial scales using UAV and satellite observations in agricultural landscapes. So let's start with the definition of fractional vegetation cover, which is the percentage of the vegetation covering a surface unit. And fractional vegetation cover regulates the land surface temperature and so shading and evapotranspiration. And both of these variables are very important for hydrologic, climatic, and geochemical cycles. We can monitor with these variables with different remote sensing platforms, but integrating these platforms remains challenging. So the objective of this study will be to generate the fractional vegetation cover from UAV RGB imagery using machine learning models, and then explore the association of fractional vegetation cover and FBC from field photos and UAV, and to model the satellite fractional vegetation cover where UAV data will be used as a reference. And then finally we'll explore the fractional vegetation cover and LS3 relationships across platforms. So we have two 15-hectare sites in Kenya, Taita Taveta County, and one of the site is in highland and is dominated by mostly vegetable cultivations, and these are characterized by very small fields. And in Makta we have a bit larger fields, but it is in lowlands, so we have kind of two different landscapes. And so we have performed two UAV campaigns in 2024 and 2025, and in both sides almost the same time, and there was of course crops growing that time, and we have thermal and RGB from the UAV, and then we have also collected satellite imageries from 3 different platforms, Planetoscope at 3 meters, Sentinel-2 at 10, and then Landsat 8 and 9 at 30 meter resolution, and we have LST from Sentinel-8 and 9. And all the satellite images were collected almost like a week of the UAV acquisition. So first we have the UAV RGB images, then we apply machine learning models to generate the reference fractional vegetation cover, which will be later fed to satellite model, BC modeling. Then we have UAV LST, and then we first assess the relationship within the UAV, so FBC and LST relationship, and then we have satellite images in different platforms. Then using the machine learning models, generate the satellite fractional vegetation cover, where we'll be using the UAV data for reference that as I mentioned before. Then we have satellite LST from Landsat, and we then check the relationship with the LST and FBC. So we collected validation photos using the digital camera, And we applied very simple also threshold algorithms, where you can see here there it's quite straightforward, and it generates the fractional vegetation cover from each image. And this is the sampling strategies that I followed, and using 30 meter by 30 meter grid and 10 samples within one grid. And then to reduce the autocorrelation effects, we had this group k-fold validation approach. And this is the outcome of the UAV fractional vegetation modeling for both sides. All the three models we tested with random forest extreme gradient boost and support vector machine, and they perform quite similarly. And as you can see from the model accuracy, but random forest has the highest accuracy across all the models. And so we used the validation of the UAV data is we captured the images, then we generated fractional vegetation cover from it, and then we compared it with the UAV within that footprint. And it's very interesting to see that if the in the left side, if you see if there is a low and sparse vegetation, then it is underestimated by UAV, which is not surprising. And but while it is in the dense vegetation cover, you see for example, in the field it is like 43%, but in UAV it is detecting like 98%. And also from the regression plot, you can see that there is a shift. And now this is the fractional vegetation cover and LST within one side, and we wanted to see if there is any change of relationship when we are looking at different scale. So this is not satellite, this is from UAV, but we are looking at different scale. But there is not much differences when we are looking at three different scales. So then we had this satellite fractional vegetation modeling. We used random forest for this. And you see the Landsat performed quite well, Landsat and Sentinel-2. But PlanetScope, although it has better spatial resolution, but it performed poorly because it is quite, the pixels are quite heterogeneous, and also it doesn't have shortwave infrared, I think, which was one of the reasons. And this is the model output from random forest and Landsat 8, and in B panel you can see the LST that we acquired from Landsat 8. And then we masked out the other landscape, only taking into consideration the agricultural lands. So there you can see there's a strong, this moderate negative relationship between LST and FVC. And that's in the 2025, we see the similar pattern. So this is kind of ongoing, and still the work is going on. So now I'm trying to find if this, because there is a lot of topographical differences, so how it is playing a role here. So we have UAV-based vegetation classification with very good accuracy, and there is a strong agreement with the field collected images, and then we have satellite-derived FVC, we found very good accuracy from Landsat 8. And then we have moderate to strong correlation within the UAV FBC LST relationship, and moderate FBC LST relationship within the satellite images. And this UAV RGB imagery have strong potential for high resolution vegetation cover mapping, and this kind of cross-scale FBC LST analysis highlights that the role of vegetation cover regulating the surface temperature, and it is very important for different cropping practice, where we practice like cover crops, which is very important for this kind of landscape in Africa. Okay, thank you.
Thank you, Asfak, for the very interesting talk. Would there be questions from the audience, please? Ilkka, please.
When you measured with the camera from short distance, the cover percentage, did you verify that it's not subject to bias by using some other means?
By others means you mean like shadow or
like point sampling?
Okay, so yeah, so we captured those field photos with the digital camera. I don't know if that's what you mean. So there we tried to check if there is a shadow effect, because there is also canopy under the canopy, and there is like shadows. And while applying this excess grain index, and we somehow eliminated it, but there is still some errors, which we are trying to address as well, like manually doing it, rather than just putting it into the model. Thank you.
Okay, thank you. More from the audience? I would have one, if you don't mind. Were you surprised about this PlanetScope not performing so good? You said the reasons were like it was heterogeneous vegetation
Yes.
and stuff, but I mean, I was a bit surprised.
Yeah, it was also very surprising for me. But the study area, it is very, very heterogeneous, because there's a lot of going on. It's not like a single species, so a lot of going on, and then you have similar fractional vegetation cover for many pixels there, and those are so there is also background that is like the soil type is always changing within one site I'm talking about. So it is introducing a lot of noise or variations, even though they have similar fractional vegetation cover. But in Landsat 8 and Sentinel-2, the noise or the variation is pretty much canceling out each other. It has more stable spectral signals. But in PlanetScope, it is very noisy sometimes. So that could be the reason why it is performing better. But it doesn't mean that the maps from PlanetScope, they are bad. I have checked them and compared with it. So the results, okay, it is because there is more noise. That's why there is this accuracy is not good. But in reality, the maps are produced by it. It's quite good. Yeah. Okay. Thanks.
Thanks. Okay. If there are no more questions, I'm ready to thank you, Ashak, once again. Yeah. And then I want to thank you for sticking around. I want to thank the Olli and you all for listening, and the tech guys here in the front and in the back. Well done. And yeah. Yeah, wish you all a nice evening. Thank you.